Вообще, конечно, я что думаю, может быть, мы все-таки действительно просто первую лекцию пропустим, но боимся, по сути, начала девушки. И я боюсь, что просто время там полчаса. Да? Ну давайте, да, тогда давайте тогда сейчас. Все, тогда запускаемся, да? Все. Да, Сереж? Да, Сереж? Нет, мы еще не начинали. У нас накладка с да не очень. Хорошо. Нет, я почту прислал на Zoom. Канал транслирует. Сегодня. Сегодня 8:26 я прислал ссылку на нефтекамеру. Что касается школы, там только моя комната, то есть я ее даже не вижу. Все, слушай, сейчас мне звонит Егор, дайте еще перезвонить. Алло, да. Алло. Да. Че? Я понял. Ну, давайте так сделаем. Я скажу, что вот эта лекция просто отменяет, чтобы не гнать вот это вот все. А в 15:30 начнем по графику. Все, да, договорились. Хорошо, все слишком. Алло. Нет лекций никаких, и возможно не будет. И возможно, нам не нужен будет переводчик. Я сам пытаюсь ответить сегодня до середины дня, там, 2 часа.
How was your weekend? It's very fun. Learning a lot, but at times nothing.
Просто я видела,
بعدين بعيدين ده والله استنى ما يحصلش ماشي
Да, слушай, ну я робот ставил промпт. Начал паниковать, нервничать. Все по плану, просто тень. Слушай, посмотри, пожалуйста, себе у тебя нету еще 2 листочков наших магистратов. Не все, то точно. Есть? Слушай, я 2 не нашел. Хорошо, сейчас. А там кто написан? Кто чье? Все отлично.
Okay, you are. Yeah.
There are
Let's record it. So it's good. I was I should watch it. Ah, really? Oh. It's from today? Yeah. Because people see.
Like you.
Okay. I'm not asking the restaurant. You're selling or not? Yes, everybody is selling. Since you got a hot I will leave tomorrow morning. I will sign the table. And I will I will just sign. Yes, you can. Yazı tura. Aynı yerde oluyormuş bir de. Here's the invitation from the St. Petersburg. At the same day, PVR and another one. What's PVR? I have also. Right down. I'm sorry, come on. This year, 45 days I live in Russia. 45 days. If I live one more week, it will be 2 weeks, 3 weeks. They will give me Russian passport. Okay, I tell you. Many international channels. Like Russia. You can go. In my territory. Что говоришь, 200,000 Russians. Just I'm leaving. Okay, Professor, please tell me the file. For lectures.
It's like art is my brother.
Okay.
IT is not any individual programs. You don't have to study. It has a mathematics background, at least like a good programming skill, coding, and do not need at all to study. So many IT courses are good IT courses or math courses. And all my IT courses, everyone was studying. All courses run also like what is there are no such IDs, but there is no such called First one, just my boss.
Hello, do you hear me? Do you hear me? Hello? Guys?
Yes, hello, good morning.
Hello? Good morning.
Good morning, Andre.
So let's start.
Can you all hear me?
Yeah, perfect.
Okay. So you want me to start right now?
Yeah.
Yeah, okay, let's go. Let's try to share my screen and make sure that everything is working appropriately. Okay. Can you confirm me what you're seeing right now? Are you seeing like the first page of the presentation?
We see first stage of the presentation and comments also.
Comments also. So let's try to just change another thing. Instead of sharing the file, I will show the screen. Now you're seeing the comments too, I think. So if I do this, probably, are you seeing the presentation right now? Yeah. Okay, great. So let's start.
Yeah.
First of all, let me introduce myself. I'm Joan Masuet. I'm a structural engineer. I work in IDOM, and I've been working in this company for the last, I think, for the past 14 years. I have, right now I'm the digital transformation manager in the nuclear services department. In this department, we are like around 250, 300 people. I'm not sure right now. We're growing, so it's difficult to tell. I have 18 years of professional experience, and 10 of them are in the nuclear sector. Particularly, I'm proud to say that of these 10 years, 7 of them I have spent them working on site on construction projects such the ones that you can see below. The question is why a structural engineer is working in digital transformation. And so the key point here is that because of my understanding of construction processes and project management, I was involved in digital transformation to see how digital tools could help in our processes and in construction, the commissioning processes. So that's the reason why my boss told me if I could do this class today. Okay, just let me move something in my screen. Just give me a second because it's covering some of my important notes. Okay, so when my boss told me to do this session, my first thought was, okay, what can I explain in just 1 hour? Because there's a lot of software and technologies that are available to help the commissioning. And in 1 hour, I would think it's no sense to explain what can be done. So I ended up with an idea. This is the one that I'm going to propose to you right now, is to through a business case, which is not real, but an imaginary situation, to be able to see how digital tools are able or are there to help people to do their jobs more easily in the commissioning. So what we're going to do is we're going to see an interaction of different people and see how they interact, how they share comments and things, and how they are using digital tools to give an answer to the problems that they are involved in. Obviously, we are going to see only a small part of digital, but I think it's going to be enough to give you an idea of what can be done. So before I start, just a couple of comments. First one is since I'm presenting, it's difficult for me to see if there are raised hands. So I encourage you to interrupt me whenever you have a question. And second one, obviously, interrupt me because it will be more interactive. Do not hesitate to stop me and ask whatever it's important for you to understand. Okay. Okay, let's go. This is the start of my imaginary case, not my business case, the one I'm proposing to you. We have Mr. Reed. Let's say that he is CEO of a company that I've called a dismantling company. Let's say that this dismantling company has like 73 nuclear reactors that are operating, that many of them are over 40 years old. So somehow he knows that they are going to be shut down in the near future, and obviously he needs a plan. I mean, he says, okay, I have a problem, I have to manage all this. What can I do? What he does is he says, okay, best people for the biggest problems. I do have a problem here. He calls Mr. Osorio. He's one of his senior managers, and obviously he's got some professional experience in oil and gas and decommissioning. So his ideas, his lessons learned are worth to hear. And he goes to him and asks clear questions. We need a plan to dismantle our nuclear fleet. What shall we do? Obviously, Mr. Osorio he gets the point of his boss. He says, okay, what can we do? I have to think about something. So based on his professional experience, he defined his top priorities. I mean, he says, okay, I've been both in dismantling before. So I know that there are key issues that I have to deal with. I need a reliable bill of materials. I need to know what I have to dismantle in clear numbers. Obviously, because it's nuclear, I've been involved in oil and gas, but it's nuclear, so I know that radiological inventory is important, and I know that the cost of radiological materials increase significantly compared to the others. He says, I need a consistent planning with all these volume bill of materials that I do have to manage. I have to estimate labor, and with all this information, prepare accurate cost. That is some of the things that my boss will require to understand. And after having clear costs, I need people to do this. So I need a robust network of people, of companies that will help in my process. And obviously, I have to ensure that I analyze the best alternative at any time, and that I have, I would say, an efficient risk identification process, ensuring that I have no surprises whenever I start my decommissioning activities. So there's a lot of stuff on his mind, and the first question is, okay, where do I start? I have a lot of things to do, but where do I start? So what he does is, for some days, he thinks on how better he can approach the decommissioning of a nuclear facility. Then he does some research and shares ideas with some colleagues. He goes to the company lessons learned database. He checks experiences in the past for suggestions for things to prevent. And finally, he gathers all his thoughts and ideas, and he decides to start with a risk management process. So obviously, a risk is something that may occur and that can affect your project goals, but it's also something that appropriately managed can be an opportunity. So he goes with this theory to the process of his company, and he decides that at first he needs to identify all the risks that he's got. Then he needs to analyze the impact of this risk, the probability of this risk, how he can manage all. Then, no?
Excuse me, Mr. John.
Yes.
So in the 2 slides before, please.
I cannot hear very well. It's very soft, the volume here. If you can speak louder, it will help me.
You can start.
Okay, I will try. So in the two slides before, if we go to the graph, 2 slides before.
This one?
No, previous, please. Previous. Yes. So in the whole decommissioning process, when is the time factor? It's not necessary to have a target that within this amount of time frame, we have to complete, we have, from the initiation of to complete these installations, there must be a time frame, or it's not important.
I apologize, but it's very difficult for me to understand this. I can understand.
I try. Am I audible right now?
Yeah. Thank you.
So where is there also a time frame necessary for the decommissioning to have a target starting from initiation to complete these installations?
Yeah, there's always a target that you may have.
So where is that? Where we can?
It's not presented here. We could say that consistent planning, when you are doing planning, let me show, just give me a second. I need that pointer. Just here it is. Can you see my pointer right now? Yes.
Yes.
When we say consistent planning is an activity that involves different constraints. One of the constraints will be this time frame target. So if you have a very close time frame, you have to prepare a consistent planning that involves more labor activities or more subcontracting activities. No? I mean, you have to manage labor estimates with your available planning. Obviously, it has to be something realistic. There's a saying in Spanish that says, I would say a clock fabricator can provide a clock in 1 year, but in 365 days, no? But not 365 clock makers can provide a clock in a single day. So the planning has to be consistent with your constraints and realistic. But if it is, I mean, dealing with labor estimates, you can have more I will say, compact planning than if it's required. I don't know if I'm answering right your question.
Yes, sir, yes. So the time and the cost, they are directly related. So
always. I mean, all these activities are related between them. That's why I put them together. I mean, there are more things that may worry you when you are decommissioning, but obviously I would say the materials estimates, labor and costs are all related with planning, and vice versa. I mean, if you need to do things faster, probably it will cost you more. If you have more time, maybe it's cheaper. If you have everything in your bill of materials, then you may have deviations in your schedule. So the relation here, it's very important to have a clear understanding of how it works. Yeah.
thank you.
So let's go on. We were, just give me a second, we were in here. We were evaluating risk. And then what he does is he evaluates, I mean, the impact of this risk on the goals that were told to him, and he decides, or he has to manage some solutions, some I would say contingency and mitigation plans or activities to deal with this risk identified. So let's go. First tool that he uses, and here is where we start speaking about digital tools, is he goes to register his, I would say, risk. No? Right now, we're seeing like a digital process of risk management. This is a kind of tiles that we have to manage with a common project. It's a standard structure in IDOM projects. No? So if we start with a short video, we can see that Mr. Osorio goes to the risk management tool. He's got a database here in SharePoint. This database is linked to a panel where he's got a classification of the risk, the impact, the categories, the risk management, the status of these risks, and he can get dynamic information by clicking on each of the entries and deal with the contents. You can see that there's a list that he can open new risk, and one by one, he starts gathering his thoughts, clicking what is worrying him, and registering descriptions, activities, assigning processes to, or I would say activities to some of his mates or people that is working in his team, classifying the information and getting ready to start with the, I would say, tasks that he assigns in this table. This is just an example. It could be used, I would say, for risk, but also could be used for other things like lessons learned or other things. Okay, let's let the video finish. I think it's almost done. If you check here on the right side, you will see always this round circle. I'm trying to propose you whenever I speak about anything where we are talking or about what we are talking. You can see that right now we're talking about this, and maybe I won't tell you afterwards, but you will see that the blue mark is changing according to what is the key point that we are dealing with. Okay? So among all the risks that he has registered, Mr. Osorio thinks that the schedule and cost deviation are two of the major problems that he's got. So he decided to start with his mitigation plan regarding these two activities. Again, he thinks that okay, what can I do with these deviations? He says that obviously, if he wants to prevent schedule deviations and cost deviation, he's sure that he needs a very accurate and reliable bill of materials. But he's got a problem. He knows that in nuclear, everybody has been told that the design requirements, facility configuration information, and real configuration must conform. But obviously, after 40 years of operation, these three elements do not conform. So he's got drawings to start with. I mean, he's got 40 years old drawings. In best cases, these drawings are PDF files or CAD files, but it's not very reliable information. So as I said, it's not precise, maybe it's incomplete, or even if you compare what is said in the drawings with the reality, it's not consistent. And if he wants to start extracting information for these drawings, obviously he needs a lot of man hours to be involved. No? He needs a bill of materials from PDF files. He needs to have a staff of people just checking and taking notes and billing or listing what they are seeing in the drawings. Obviously, nowadays this is not working this way. We work with BIM designs, with 3D models. We work with digital data, but he has to deal with something that is not digital yet. So he's heard about digital. He's heard about all these things. So he starts to think, what can he do? So he says, okay, let's decide what is the risk. First risk is say, okay, I want to prevent schedule and cost deviations. This is my risk. Okay, so what can I do with my risk? No? So I need to have a reliable bill of materials. He's got a clear idea of this. No? But the key question is how? No? So he decides that after being in some chats or I would say congresses, he thinks that exploring the use of digital twins for existing cassettes could be useful. No? He knows that for new assets it's clear, but he's heard that for existing assets there's also alternatives. So he decides to appoint a responsible. He calls to his mate, is Mr. Hueso, and tells him, okay, I need a mitigation plan in here. So please check what digital twins are and how can be used in decommissioning. So Mr. Hueso, he goes to the dismantling company procurement database. He knows a little bit of BIM, but he's sure that some people has been working in the company before. So he wants to check if there is references in there. He needs some support. He wants to have solutions for this. He wants to know what a digital twin is. So I want to have a clear idea of what a digital twin is. I want to know if it's possible to produce a digital twin of an operating reactor. I know that I can do it for a new one, but what about an operating one? And he's got the key goals that his boss has transferred to him. We need to provide a reliable bill of materials, and we need to get a reliable inventory of what is radiological material and what is not radiological material. So he goes to the database of his company. We're going to see now another video. As you can see on the right side, we have this procurement icon right now. So we're going to see something related to procurement. He goes to the company database. This is also IDOM information for you to know. He goes to the supplier list. He just goes to the search button. He searches for the concept BIM, and automatically he's got a bunch of suppliers that are telling that they provide BIM support. He selects one of the suppliers according to the marks that previous workers had assigned to this cooperator. He checks some information. He's got the contact. He's got I would say, telephone numbers, emails, whatever he needs to start with the first approach. Okay, after checking the database and after checking different suppliers, he decides to call, we will say, Area B. Okay, this is the company name, company that is working in BIM. Okay, and he approaches the company, and with the questions that we have seen before, he requests a presentation, and that's what I will say that, as you can see on the top, that this mantling company supplier, Area BIM in this case, is going to tell. It says, okay, what a digital twin is. So they give the clear answer. No? Say a digital twin is a virtual representation that serves as a real-time counterpart of a physical object or process. And then he asks, is it possible to produce a digital twin of an operating reactor? And this company says, yes, digital twins can be produced based on existing reality. I mean, from reality to digital, through very clear 3 steps, we can get a digital twin. First, we need the physical reality. Then we can capture this reality using different tools. And afterwards, with these specialized softwares, we can provide a digital twin. Now what we're going to see is some of the things that this supplier tells Mr. Hueso. No? So how is it made? So we have the reality. These are business cases. You can see on below on the bottom part of the slide. It is as real experiences for 2 companies, nuclear companies. Enusa is a fuel supplier, and ANAF is a nuclear operator. So these are the 2 references you see. You can see in this case on the left side is reality. This is magazines for fuel pins, nuclear fuel pins. We go there, we scan this digital reality, we produce kind of digital environment, and then with this digital environment, we can proceed with a digital twin. Okay, so Mr. Hueso says, okay, it's clear, but how does it look like? So now what we're gonna see is we're gonna see kind of a video. This is a electrical room in a nuclear power plant. We will see what we're seeing right now is a real picture, and we'll see through a couple of videos how this picture becomes a model. No? Okay, sorry, just. As you can see, what we've done is we've done a scanning of the room. So we've got, we're using kind of, we say laser scan, that it's sending millions of signals to the environment. He receives back geometries and it creates what is called a point cloud. The point cloud allows you to afterwards create this model and transfer the information that initially was just points to elements. Let's see after the video, just a couple of seconds more, it's finished. And with this, I would say geometries converted to elements, we can start getting information attached to the elements. So as you can see, we can have information linked. So cable trays are not anymore just lines. They become cable trays with information attached like material, volume, weight, radiological characterization, and the same for any other element on the room. So as I said, geometries become elements. Elements have information linked. And elements has also documentation attached. So we can attach or link to this element like dismantling procedures or instructions, or I will say certificates or whatever it's required. Okay, let's go on. Okay, we now have the geometries, but the dismantling, the supplier also says, okay, but BIM is not only geometries, it's also a good tool to deal with planning, labor, scheduling, and also managing some constraints. No? So,
one question from our student.
Previous slide, please.
Sorry?
Previous slides, please.
This one?
Yes, when we convert the 3D scanning, how you convert the geometries into elements, but how you introduce the weightage.
How you introduce what, sorry?
Weight, different parameters.
Yeah, okay, since...
You see, we have trillions of point clouds, and you have to introduce weight. You already mentioned also. So, what are the criteria? How you choose the weight is to different factors, and how you make the parameterization.
Okay, this will be kind of. Let's do something. Can we mark these questions and explain you afterwards? Because at the end of the presentation, I have a kind of support information. I'm going to show you these slides at the end. But the key thing is there is specific software to deal with this. No? And instead of cutting right now the presentation and going to these slides, just I'm taking the note of your question, and if I forget, just remind me at the end. Okay. Yeah, is it okay for you?
Yes, please.
Okay. So let's go on. As I told you, the company is telling them it's not only a bill of materials. These digital twins can also help you dealing with the schedule. There's specific software in the market that in which linking, I would say, Microsoft Project or Primavera or any other planning software with these models, you can do like a 4D, it's what is called 4D, it's linking geometries with timelines, no? And deal with your schedule of your project. Now we're going to see another video. As you can see, now we're dealing with labor and and I wanted to have the pointer and I see that it's not working. As you can see, we have labor and planning. So what we're going to see is another video in which, using different softwares, there's kind of relation, and we can see how our activities, in this case, is construction activities, but if you do in the reverse way, obviously, this will be decommission activities. This is not a commercial video. This is real, I would say, images taken from the software directly. You can see like the cranes moving and the relation of these displacements with the schedule. Okay, let's go on. Okay, it's very good, but I've heard about virtual reality. Is it possible to have virtual reality with these digital twins? And the supplier says yes, sure. I mean, it's not a direct process, but if it's important and if you have, I would say, very specific and critical processes like dealing with, I will say, the nuclear fuel, we can help you with some virtual environments that will help you train your people. So they go and they show you them a video in which we can see the real situation. And then with the virtual environments, what can be done to train these people outside the radiological area without receiving doses, checking. No? You can see on the bottom part the people on the training area, but on the top, I mean, you have seen the video of what they are seeing. Okay? Everything looks very interesting, so they keep going on the meeting. and say, okay, but I have a problem. Mr. Hueso tells this company that my people is not trained to deal with BIM software. So you're telling me a lot of things that probably involve critical software for me, and I'm not sure if we will be able to get I would say a learning curve fast enough to deal with the problems that we have to deal. Say, okay, no problem that this supplier tells them. We can provide web applications where we link these BIM models with the information you need. So we link external databases with models without having to have the understanding of specific software. So we see here another example. This is also for a real project. As you can see, I've marked a lot of activities in here, but because we're going to see an example, but it can be linked any information we want. What we can see here is it's, I would say, nuclear systems, and around the systems, there's information linked to penetrations of the systems to different areas. So this is what we call a penetrations database. And if I just put the video, this is just a web link. And without knowing anything about BIM, I have the model accessible, and I have a bunch of information that if I click in here, there's dynamic relations between geometries and data. So if I select the cryostat, I can see the cryostat. If I select anything else, I can see different elements. And as you can see, the tables and the information is changing accordingly. So in fact, for decommission, we could use such a tool to check the status of what is currently dismantled, what is pending to be dismantled the next week, or what is radiological and what is not radiological, and even to check the cost of dismantling any part of whatever is in there. Okay, let's move on. I think the video is not finished, but I think I can skip it. Okay. Mr. Hueso goes to the company and tells them, okay, I see there's a lot of potential, but I think it will take for me a lot of time to produce a digital twin of I would say my 73 nuclear units that are currently running. So what can I do that it's faster and cheaper? Because I need to start right now. I mean, I cannot wait until my information is ready. So the company tells Mr. Hueso, it's okay if we have a diagram with comparing the return and investment of my efforts. The supplier tells him, okay, you have the reality. Obviously, you need to proceed with reality capture if you have if you want to have a BIM model. So you have to scan, do this laser scanning or these 360 panorama pictures that we have seen before. And with this information, you can create a digital twin or virtual reality environments. But there's something that you can do also. I mean, you can take these laser scans and with a very, very small investment, just create what is called a plan viewer, something that allows you to understand the real or the physical reality of your environment without having a BIM model. Mr. Hueso says, okay, it sounds good to me, but I don't understand it all. Can you explain a little bit more? So the company just shows another video. This one has sound attached. I don't know if it's too loud for you, because for me it's sounding loud, but if it's too noisy, just let me know, or if you can manage the volume yourself, it's perfect. Otherwise, just let me know and I will try to do it myself. Okay?
The Digital Plant Viewer is a web-based application that provides a simple plant map with embedded icons, including 360-degree images, live video feeds, live RP surveys, and wireless telemetry for plant temperatures and dose rates. In addition to the maps, other tools are available on the web page, which provide a single portal to complete other tasks, such as accessing LMS, passport, or shift logs. This is a pre-job brief in progress. The supervisor is using Digital Plant Viewer to review walking paths and review hazards that could be in the area where work is about to be performed.
Can you show us where our safe travel path would be so we can keep our dose as low as possible?
We'll come along the back end, come through here, maintain our dose as low as possible.
By conducting the brief with the Digital Plant Viewer, it enables the workers to ask questions and discuss the work plan prior to going out into the plant. This supervisor is in the field with his crew, but he is able to respond to a question from another location.
Hello, it's Tim. Oh yeah, just go to the Digital Plant Viewer, go to the home page, 69 foot, go to the aux building.
The Digital Plant Viewer enables him to review the work in progress at the other job site and answer the questions without leaving his team. The RP desk is a busy hub where workers wait in line to obtain survey information and ask questions about the area in which they need to go to perform work. The Digital Plant Viewer helps to alleviate the wait time by simply checking the touchscreen for information and surveys that are embedded within the tool. In addition, Digital Plant Viewer can be used by plant personnel to guide visiting personnel to their destination utilizing the integrated plant-wide maps. The Outage Control Center is using the Digital Plant Viewer to monitor the progress of work in the plant with live video feeds and telemetry. OCC personnel can view the progress of work in the field and report out immediate status to the entire team. In addition, they can also see live dose rates and temperatures in the field. This saves time and dose by not physically going into the plant to check progress.
Could you hear the video, the sound?
Yeah.
Yeah. Okay. So it's clear that the digital twin provides Mr. Weso with the bill of materials, but thanks to other tools like this digital plan viewers, he can start just preparing the jobs, analyzing the geometries, getting suppliers involved. And even if the bill of material is not closed yet, he can start working. Okay. And also they say, okay, because everything on this digital solution that we have seen up to the moment, it's information. We can just go onto this information and can start doing digital analytics. No? We can report digitally and automatically what is done. In this case, what we can see is an application that it's used to, I would say, to report the progress of a digital twin, or I would say plan viewer production, in which people go on field, they do their jobs and they report to a mobile application what they have done, and automatically the project manager receives the information on his control panel. So you can see in a video, I mean, this is to report progress on digitalizing the plan, but could be used to report dismantling activities. So like, okay, the activity is done, and then the graphs and the information, it's actualized accordingly. Okay, it's pretty short. We're gonna go through this global overview where they can have like progress information or even tables or information of what is done or what is gonna be done next week or whatever. Okay, let's go on. After this session with this supplier, Mr. Weso say, okay, I know the conclusions right now. Digital twins are an effective tool, an efficient tool too, for bill of materials, for radiological inventory, for planning, for labor and cost estimates, for progress monitoring, for training and safety, and many more. And obviously, I've understood that I can get a digital twin of something that is existing. I do not need to have a new element to start with a digital twin. So the final result is that Mr. Hueso says, okay, I know the conclusions and I'm going to report them. So he reports to Mr. Osorio and tells him, I think digital twins, as you first thought, are a good tool. And I encourage you to start pushing with this as a mitigation plan for all the costs and risk and schedule deviation, sorry. So after the analysis performed, Mr. Osorio is certain that an essential tool for the success of the dismantling project is the use of digital twins, and he defines the roadmap that he wants to follow. Then he gets to Mr. Ruiz and reports his conclusion. And Mr. Ruiz, sorry, I was hearing a kind of noise here. Mr. Ruiz relies a lot on the insight received from Mr. Osorio, and he formalized a contractual relation with Area BIM to start producing digital twins for all his nuclear fleet and implement these digital solutions that were explained to him to exploit the data efficiently. Okay. So after seeing all these kind of, I would say, symbolic explanation of a typical process in dismantling, the conclusions of the session will be the following one. I mean, digital technologies are useful, and because they provide efficient solutions, they are and they will be present in many decommissioning activities and processes. And I would say they will be because every day these solutions are cheaper and cheaper. And since they become cheaper, they are more frequently used. We have seen that we can use databases, we can use reality capture, we can use digital plant viewers that take advantage of these reality captures at low cost. We have seen that we can have BIM models that are produced from these captures. These models provide accurate bill of materials, radiological inventories. We know now that these BIM models can be linked and provide the commissioning planning in 4D. We know that we can progress or monitor the progress without automatic KPI reported through mobile applications. And we can also use these BIM models to check maneuverings or critical activities in dismantling. We have also seen that we can use these BIM models to provide virtual reality environments that are useful for trainings in critical activities. We have seen also that, we haven't seen, but there's also other activities like we can do artificial intelligence with the data that it's linked to these BIM models. We can do, as we said before, mobile applications. We can have robotics to deal with very critical radiological stuff. We can do some data analytics on the information produced and many more. I mean, as I said at the very start of the session, we could spend 1 month speaking about digital and we wouldn't have end. So I will say the conclusion of all this is that, and the idea that I would like to have is that before any decommission activity, what you have to do is always analyze what technologies could be applied for a better performance. There's always new technologies appearing on the market. So a market survey and counting on specialized companies to support you is very relevant and very productive. And if you get out of this session with this idea, I think it's the goal of the session. It's obtained. It's reached. And that's all. That's all from my part. Before I open questions to the rest of the people, I have this software question from your colleague in here. I'm sorry you didn't introduce yourself, so I cannot call you by your name. But if you let me, I will try to go back to the, I will say, common format. And if I go here, I think, no, here. And I go back to presentation. Correct me if I didn't get your question right, but you asked me how from a point cloud information we could get elements and information like weight attached to these elements. So what I've told you is, I would say the market provides you a lot of different softwares that deals with these point clouds, especially these three model softwares. I mean, there's this kind of, I would say, a specialized software that uses as input these point clouds. What you have to do is you have to use these point clouds as a base in which you start drawing on top. And if you draw on top of these point clouds using this software, you can see here, sorry, my pointer, it's gone. Just let me switch it on again. Here, using software like these ones, you convert these points into geometries that inside these softwares are also converted to elements. Whenever you have an element, you can attach information to this element. So you can say this element is made of, we'll say, stainless steel. And when you say stainless steel, the internal database of the software knows the resistance of the material, knows the weight of the material, knows some basic characteristics of this material. So according to the volume of the element and the, I would say, cubic meter weight of the element, he can give you as output directly without human intervention the weight of this element. So this is important because using these softwares, you extract, I would say, volumes and weights of whatever you have to dismantle. Did I answer your question?
Okay, so if I compare these slides versus the last slides, then okay, I have intergraph which for 3D visualization on scanning, 3D scanning intergraph. SolidWorks is for the 3D visualizations. We have Oracle for the database, ANSYS for the again 3D visualization. There are just slides which you show about the radiological informations and SAP. But where is the information for the weighting? To provide the weight, it is a manual work. It's a person has to explicitly assign during the point cloud to use artificial intelligence and do the classifications. We need explicit information, and explicitly we have to assign a particular weight to particular information. That has to be synchronized with each and every individual models, every individual objects to be dealt with SolidWorks or ANSYS.
Okay, let's go to another slide to try to explain you this.
The last one.
This is a real configuration of software architecture for a real project. I mean, you don't work with all these softwares in here every time. So you define a data and software strategy for the goals you are seeking. Not all the softwares are good or as good as others for specific activities. Let's say for piping, there's some software that are better, especially if it's design piping. But if you go to dismantling, maybe it's better to have other softwares because the design information is not relevant for you. You only need geometries. Or if you want to do civil works, you have other softwares that are better than the others. So whenever you start a project, you decide which is the software that you want to use and how this software interacts. If you start with a digital twin that is coming from reality, you do some scanning before. I would say this scanning is let me say the word, it's idiot. No? It's just geometries. You can take measurements in there, but you don't have elements. You just have geometries. You can check distances. You can see that something is a pipe, but if you click into this pipe, it's just a point. It's not, it's saying anything. It's just point. It says like 2 meters, but 2 meters of what? No, because you're seeing a 360 picture, you can know that it's a pipe. So if you want this pipe to become an element, you have to go to this BIM model. If you go to the BIM model, you need obviously human force in there. You need BIM modelers. These BIM modelers are engineers that can or that can easily understand what is a pipe and what is a wall, what is everything. So what they have to do is they need to have the drawings, the PDF drawings that we've said at the very beginning of the session that Mr. Osorio knows that he has to deal with, all drawings. But in this drawing, the information, it's good enough to understand what materials are in there. So using the drawing in one side and the point clouds on the other, he decides what is a pipe and what's not. And say, okay, this is a pipe. And to check the material of this pipe, he goes to the drawing. He checks the data that it's next to the drawing, saying this pipe is made of, I would say, common steel, carbon steel. Say, okay, so he marks the pipe as carbon steel. The software has a database where they have materials in there. So when he says this is carbon steel, automatically the weight is assigned and the rest of activity is assigned. No?
Yes, yes. Now it is clear. So if we go to the last slides, please remember what you have just explained. If you go to the last slide, please.
Which one?
The last one.
This one?
Yes. So you already explained that we have informations. So when we have artificial intelligence, we have here the scenario you explained is a supervised classification because we have already a lot of information about the object. So it's a supervised classification. So my exact question is, we have database system, you have Oracle, you have reality capture from 3D printing and 3D scanning and intergraph, and you have also 3D reality. So to bring this information from Oracle database on 3D point cloud, million of point clouds, at the same time we have supervised classifications. We have the information of the object, and we have information about how much importance this have in the point cloud. This between there is a weightage to be introduced individually with respect to different object. How that has to be introduced manually, or you have a definitive software for that. For coming from database on the 3D point cloud to artificial intelligence.
Give me a second, I want to go back to this slide.
Because it's not a software job, it's no software. Yes, this is for example SolidWorks.
It's very easy. It's just an informatics issue. No? I mean, when you create an element into a BIM model, you create an element that has an ID, a unique ID attached. So having this geometry ID linked to whatever you want to link it to, this is an automatic link. So if you have a database, I would say of, in this case, penetration information. No? As you can see, there's a lot of information here. This information is maybe the material, the last inspection of the penetration. I mean, the properties, if it can seal like gas, water, or fire. Who installed it, the documentation of or certificates of the installation. So all this information, it's related to one single ID. So having this single ID linked to the model, you have an automatic link within geometries and information. So the idea is you don't have to manually introduce everything in the model. Having only the ID, you can work outside the model. You perform artificial intelligence, you perform all these activities you are talking about outside the model. In fact, this is just a visualization using web applications in which you have the model. The model has an ID for each element, and this ID links to other databases outside the model, in this case, existing ones, and reports all together.
So we have a joint key in the database system linked to different informations. And according to that, you have to put weightage in the when you classify which object is how much irradiated and which object has more influence to be having more to be given more importance or attention, something like that. So there are different database and they are linked with a common key in the database Oracle, for example, and then we can. Okay, so
to give you an example related to this monthly, you have an operating plan. This plan has obviously a radiological department. This radiological department knows every hotspot of the installation. They know where they are located and how much irradiation they send to the environment.
Okay, that's clear. Yeah.
And what we do is imagine there's a valve that it's hardly irradiated and it's a real hotspot of the plant. So once you have it drawn in your 3D model, this valve has an IP. So you take this IP, you link this IP with the database of this radiological department. And automatically all the information of this hotspot, how much radiation from where it started, I don't know, I would say the lead blankets that you need to protect it, everything that it's linked, it's available. So that's why it's useful, because you don't need to repeat everything. You just take advantage of what is existing in your organization.
Thank you.
You're welcome. Okay, any other questions?
Okay. Yeah. Once more question.
Hello, my name is Cüneyt from Turkey. You already mentioned, maybe, but I missed. You have some digital technologies here, right? And these are private. I mean, these are only special for your customers, or you can share it with student use or for training purposes.
What do you mean? I don't understand your question at all. Sorry.
Okay, maybe closer. What I mean that you have some digital technologies, right? And is only for your customers that they can use, or you can open these technologies for training purposes for universities or students?
What I've shown you is what is in the market. It is not EDOM's solutions. I mean, there's a little bit of everything. What I'm trying to explain to you in this presentation is that the market offers you a lot of softwares. You need to know what you want to do and why. Once you know what you want to do and why, you can select the best software. To select what you want to do and why, there's consultancy companies, in this case like EDOM or others, that can help you through this process, because you need somebody that knows the technologies to tell you, okay, for this, better technology is this one, for this other option, better software or best software is this other. Once you've done this, you have to deal with the licensing cost of these softwares. There's university versions of licensing, for instance, ANSYS or whatever. Maybe sometimes it's free, sometimes you have to pay for them. You can always reach agreements, commercial agreements with these software providers. So if you have a kind of idea of what you want to do in your university and why, there's always an option you can find out. But the key point is to select the best software. And obviously, when you are selecting the software, costs are relevant. Just to give you an example, let me go here. Just to give an example, let's make it bigger again. If you go to 3 modeling softwares, you will see that, for instance, you have PDMS, or you have Autodesk already, or Aviva Everything 3D. So if you go in, for instance, for Aviva or PDMS, these softwares are very good for designing piping, because they have, I would say, the specifications already loaded in their internal databases. So geometries of accessories and everything, it's available to the designer. This is very good because it allows you to save you a lot of time when you are designing. But obviously, the licensing cost of this software, it's significant. No? It's more than 10 times the cost of Revit. No? For instance, Revit, it's very good dealing with geometries, but has poor databases in regards to piping design. No? So the key question is what you're going to do. Are you going to design a piping line, or are you going to dismantle a piping line? Because if you're going to dismantle a piping line, you don't need to know the geometry of the accessory, because you first will scan it, and then you just need to know the weight and the material and the volume, nothing else, or if it's radiological or not, no? Or if it's installed very high or very low, if I need some, I would say, auxiliary elements to dismantle this piece of pipe or valve. No? So when you have to decide which software is the best, if you're talking about dismantling, probably Idom will tell you, I suggest you use Revit for dismantling because it's faster, that the learning curve of the software is faster. There's more people available in the market that can use this software. So you will find easily more workforce to work on your models. And the time you will spend dealing with the models will be less. So everything will go in favor of your cost saving. Okay. But if you want to do a new installation, I will recommend you never use Revit because you spend so much time dealing with the accessories and the human error is so plausible or possible that at the end you will have overcosts during installation because you will have errors in your models. So I will recommend you to spend a little bit more in your software because you will have a better solution. Somehow, let me go to another slide that I have for support here. Somehow is what we see in this curve. We can have this curve for construction, or you have this curve also for decommissioning. So the thing is that if you are let me get my pointer. Yeah. The thing is that if you can move the common or the curve that was available with user technology from here to a previous stages of your activity, even if it's dismantling or construction, where you have the ability to influence on your costs and your solutions, it's higher, and the impact of modifications or errors, it's lesser, no? You save money. No? But if you do your engineering, say engineering when talking about decommissioning or construction, too late, because with an appropriate software, what it happens is that when you see the errors during construction or even operation, the cost to solve them, it's very high. So imagine, let's say software, no? I want to save some money selecting my software. So instead of using Aviva PDMS, I decide to use Revit for piping design. At the very beginning, it looks very nice. No? Everything, the model, the pictures are looking very well. It's great. But then you get here to the construction and you realize that an accessory, it's, I would say, 20 meters shorter than what it's really in the market. Then you have to modify all your piping design. And maybe you have already purchased the pipes and you have to delay the activity, the installation activity, and the cost of this stupid decision, it's huge compared to the cost of the license that you will have had if you have chosen PDMS at the very beginning. Did I answer your question?
Yeah. Thank you very much. Thank you.
You're welcome. Any other questions? No? If you have no other questions, I think I have a couple of videos. I thought it was appropriate to get some time because normally I have questions at the end and I'm glad to answer them. But if not, what we can do is I have a couple of videos, maybe about point clouds, to better understand you what a point cloud is and how it's created. So just give me a second to go back to the presentation. Before going to the point clouds explanation, I will give you a couple of images. Remember, you can cut me whenever you want. This is some examples, real examples. This is they are coming from a fuel fabrication facility sited in Spain. What we can say, this is the result of the point clouds. No? I mean, we go there with scanning. We scan an element. When we scan it, it looks like this. As you can see, there's kind of points you see, but this is silly information. It's just geometries. I mean, I can check distances, but nothing else. After going through the modeling process in the software that we were talking about, these geometries become elements. And once they are elements, we can assign materials, we can assign information, as we said. No? So you have like 3 examples of how it looks like after the scanning and after being modeled. Okay. I'm going to explain you shortly, I mean, how this reality capture is done. I mean, as I said, it's very important for software, for everything, to understand what you're doing and why you are doing it. It's not the same thing to do, I would say, a scanning, to have a very precise geometry check when you want to ensure that a new material is going to fit in a specific area, than just doing kind of scanning to provide you with a plan viewer, which is a tool where you just want to know how it looks like your environment and general geometry. It's not very specific. So the precision of that you have to use or the number of scans can differ quite a lot. So planning and deciding how to capture this reality, it's an important issue. After doing the scans, it's always necessary to perform, I would say, a post-processing activity, because the scans are not perfect. You need some manual activities to ensure that the results of your scans are right. And if you have these results checked and right, then you proceed with an output, and this output is the input for the 3D model. So I had the opportunity to be involved in TopFuel 2021, which is an international congress like a couple of weeks ago. And what we've done is the previous day of the presentation, we've gone to the place where the congress was meant to be done. And in a couple of hours, we decided to scan the exterior of the building and the interior of the room where we were going to do this session. So what you're going to see right now is a video of the people doing these scans in order to let you know, or to get a more realistic idea of what point clouding means.
We can select the resolution of the pictures the instrument took on site. The idea is to create as many constraints as we consider. This is doing an adjustment by least squares of all the observations. Here's our point cloud. Slice it up. In this view, we can cut this slice out. What we will do is to view everything. The size of the file is not too big, and also we normally clean all the noise and have a general view of our project and decide where to start from. So let's dive right in. Okay, let's take some measurements.
As you can see, these are silly elements.
Intensity map.
You can take measurements, but you don't know what it's brief or...
We can select a grayscale intensity map. All right, let's have a walk now. Photo is supported by the point cloud behind it.
as you can see, this is kind of just I stopped it just to explain you that first you have like a 360 high resolution panorama picture. So the image is very, very high quality. But when you want to take measurements in the back end, you have the point cloud that support this image. So what we've done in this point is just we swap the position and we pass the point clouds in front of the panorama. Now, that's why the resolution is looking different, but it is how it allows you to take measurements.
This is just points.
These are laser points, millions of them. You can see the distance between the points. Right now we see the high resolution picture too, again.
Well, the part we can see here. Let's go up there. These are the distances below.
So this is very relevant when you're going to dismantle something. If you have the capability of getting the environment geometries and restraints for any operation of moving stuff around, for machinery or cutting lines, or how big you can cut a piece of, I would say, of pipe before you move it through the corridors that are available. I mean, this is important information. And as you can see, you don't need to have a BIM model to be able to decide if you can cut a pipe in pieces of 3 meters or 5 meters, and how much it will weigh a piece of 3 meters or 5 meters, and if you will be able to deal with such a big or a small element around the facility until you get it out of there. And I think I have another example. We've seen a video of Plan B before.
1 minute, excuse me.
Mm-hmm.
So when your colleague, may I know which software you use that?
This software, sincerely, I do not remember right now. I think it was.
Okay, your colleague.
No, I will lie. If I tell you, I will lie. I can answer you afterwards if you want through an email.
Yes, but your colleague mentioned that you use least square adjustment, but you know the weakness of least square adjustment. The strength is if they have correlated data. But if it is discretized on a lot of outliers, then least square adjustment is not robust. It will take a lot of time and it will not have a high resolution. So in practice, people use Gauss-Markov model, but this is why I want to know which software it is, because the robustness and resolution depend on the algorithm. Least square adjustment is not in practice for point cloud visualization of 3D scanning. But your colleague mentioned they use least square adjustment. So may I know this, maybe later, the name of the software and which company product it is used and what is the resolutions?
Okay, if you can.
What is the accuracy of the resolutions? Maybe I can write email to you if you can.
Yeah, if you can send me an email to this address at the end of the session, I will provide you the answer for all of you. But regarding robustness, I mean, obviously this software is very robust, but it's very robust for what its purpose, which is getting geometries, not getting information. I mean,
the resolution, sorry to interrupt, the resolution includes the geometry and neighborhood relationship. So the resolution itself includes the shape, neighborhood, and geometry. So that depends on so the resolution contains this, and the resolution itself depends on the algorithm. So least square adjustment is not a good solver in such kind of things if you have a lot of outliers. And normally in 3D scanning, there's a lot of outliers, not easy to detectable from millions of data. But okay,
that's why when you want to deal with a dismantling process, the very first step is this one, but this is not the solution. I mean, obviously having a big model, it's very relevant. And it's relevant because of several things. First, using the BIM model, you can eliminate shadow areas. I mean, when you scan, there's parts that you cannot see through a camera. Imagine behind a duct or behind, I would say, HVAC duct that it's very big. Maybe you have some cable trays behind and you are not able to see them. No? So you have to complement the information you get from the scans with the information you get in the drawings. And sometimes you have to rely and assume that there will be some mistakes if you don't have enough information, not in the drawings, not in the scans. No? The key point is what is relevant to you when you are dismantling. What are the real costs? No? That's why I'm telling you from the very beginning that it's important to understand your purpose. No? You can always work with hybrid maquettes, what we call hybrid models, no? In which you mix BIM models with point clouds all together. Why? If you are dismantling an area, probably you want to know the volume and the weight and the material of the big pipes. But in a nuclear facility, you have plenty of small elements like cable routing for illumination, piping for instrumentation, which is half an inch. No? It makes no sense to spend time dealing with these elements, trying to model them, because at the end, the cost of dismantling and the time that it takes to cut them and remove them, it's so small that it's no way. But it's important to know that they are there. For instance, if you're trying to plan moving some object through an area. So if you have a small pipe in there in the middle of nowhere and you want to move something, this pipe, you have to know that it's there because you have to cut it before you do this activity. No? So the idea is that you should work with hybrid information. You model what is relevant, and the other is just geometry that support your decision making.
Thank you very much. Please show us your email, please.
Yeah, I will also try to find out a picture. I don't know if I have one in the presentation. No, I don't have it, but I will send you a picture of what that hybrid maquette is looking like. It's like BIM model mixed with point clouding, which is in fact what the market is demanding right now. I think in EDF or Fissenheim 2 reactor in Germany, it has recently performed a full hybrid maquette of its reactor, which scope was to get a reliable bill of materials to have a first of a kind dismantling project in Europe. Okay, my email, you said. Here you are. Any other questions?
No. Thank you very much.
Thank you.
You're welcome. Thank you to you all.
Thank you very much.
So, Andrei?
Yeah.
Shall I disconnect? What I can do is through Hilary, probably I would send the PDF version of this session. The videos won't be available, obviously, but we'll have the rest of the information related there and my contact in case any of you wants personal clarification or on any issue.
Okay.
Okay. Thank you so much for your time and have a nice day. Bye-bye.
Thank you. Bye-bye.
Guys, I'd like to make
Вы там понимаете, цвет, который потом мы найдем.
А все.
Она должна быть на пятницу там записана. Не на пятницу, на понедельник, надо второй. Поскольку все подряд. Надо второй на самом деле. Андрей, когда все дело, хорошее дело кончится.
Да, я...
Сумков тогда был жал, но...
Да.
So you characterize the facility, you know the materials. Something this guy was explaining just before. So you have the materials list, so you know the weights, how many tons you have to spend, the materials, and so on. You have the range of also by before the tender, it's to do this characterization, then to do a cost estimation. So how many does a cost estimation? This cost estimation enters the budget. Where the tenders are going to be. So it's really difficult to answer a question without having the information. Make this cost estimation
Хорошо.
It's not because I don't want to tell you, I didn't know all of that, so I You can have the payment assessment. You bring the car, this person looks at the car, okay, based on this car is 20,000. And then you can sell something
Просто на...
Just to take a
Еще, а дальше все уже делать. Вот это самый простой способ.
Все. А, еще есть.
Еще, да, пару минут. В принципе, я и завтра могу подъехать, но очень нежелательно. Да потому что я пообещал Михаилу, он с вами бумаги. Поэтому я, наверное, залетел.
Да, не надо, зачем? Нет никаких срочных. Так что себе это удалось побыть?
Конечно. Все в порядке.
Will take some time to So imagine the new plants, they see 6 months, but you know, I think because the problem is the materials, you know. But when they designed this place in the 60s, they didn't know. So they just thought, okay, and then now you're seeing nowadays with the new assessment methods that the materials can operate longer. Pressure vessel can operate. You already have a lot of plants working for sheet fossils. Then Switzerland and the United States are extending 6 million tons
It's the same. Yeah, Russia.
Yeah, but it's political. It's not technical.
Да, накачивает.
They have inside units. But 35 units. Yeah, 38.
So let's start, guys.
So you have 5 plants or 7? Most of them are single.
Also, guys, please wear your mask because we plan to make a photo. So photos, yeah, like Suleiman.
Good teacher for us.
Она очень беспокоится. Спасибо большое.
Do it.
I have a good example. At times all
So, dear colleagues, let's move with our lecture, which today is about cementation of solid and liquid radioactive waste. And in the decommissioning project, you mainly deal with solid radioactive waste. Mainly, it's clear because of demolitions, of dismantling of some equipment, etc. So it's mainly metals, concrete, construction materials, very different kind of materials. But also some liquid radioactive waste is also produced in the decommissioning project. It is not something absolutely unavailable because mainly of decontamination works. So it happens that some pipes, some tools, some other things are getting contaminated. It's clear that through decontamination you can release them, reuse, etc. So then, typically, very typically, the liquids are secondary waste after the decontamination. So because of that, they both are here covered for cementation, which is a method of immobilization. You remember the scheme of radioactive waste management. So many things are here. I'm not. So you will see the content. So we use the terminology which is well established. It's a glossary. It is everywhere in the IAEA documentations. It is highly recommended that you also use and follow all this terminology. So a couple of slides are about definitions. So the conditioning can be, let's say, for solid radioactive waste, you got a container and you put into the container your solid waste, so you get a package. So this is already conditioned. But for liquid radioactive waste, you cannot proceed in such a way. So you need an additional operation, which is termed immobilization, because the liquids are highly mobile. They will spill, they will contaminate everything around, etc. So here it's the text, which is exact, which is used in all kind of it's in English, but IAEA translates main IAEA publications into the official languages of International Atomic Energy Agency. Among those, there is Arabic, but there is Russian language, so you can find exact translation. Because if you do yourself the translation, you can misinterpret things, because there are synonyms and the meaning is not the same. So I'm not reading these things, but they are very much needed. So you see here also the definition of waste package. So in our imagination, we know everyone what is that. So here the photographs of the packages, but that's the container. And in the package you got your waste. You have some lining materials, some internal maybe inserts to keep the material tightly close to each other, maybe some backfilling material there. So that's then the package. And I took from France this picture again, because nowadays for a long time after internet appeared, all these things, we started to operate, judge, use icons. So we show an icon, a picture, and then in this picture there are many things much better than a sentence, and it's not so easy to capture all the sense. So you see there inside, it's so-called primary package. It's a drum which was maybe used just to collect the waste, not much as a barrier there. It's not much a barrier. And then you see something in gray color there, which is maybe a backfilling material. The container itself, it has a lid. So then altogether, this is the package, radioactive waste package. So when you do conditioning, you prepare this radioactive waste package. Okay, so very often when prepare the package, we say that we got the container, but also we got the waste form. And here is exact definition what is meant under the waste form. The last line, you see here, waste form is equal to waste form. So sometimes it is used two words, waste form. Sometimes, or even often, waste form is one word. So it's the same, the meaning is the same. So this is the waste, radioactive waste, and it's how it is after the treatment and or conditioning. So you are dealing with the solid product. Liquid is not a waste form. You are not allowed to store for a very long time, and moreover, you are not allowed to dispose it. So the waste form is a solid product. So now we can move to the immobilization, which is mainly used for liquid radioactive waste because of mobility of radionuclides. Again, here it's the exact definition. So it's when we convert the raw waste, which usually contain mobile contaminants, into a solid and stable form, which is termed waste form. And the radionuclides, which otherwise could be mobilized and circulate through biosphere, etc., the radionuclides should be somehow bound there in the waste form. And there are two possibilities. The one, it is when chemically you bind the radionuclide with a chemical bond. And that sounds, if the bond, it's a very strong one, then at a very small microscopic level of atomic sizes, you bind the radionuclide there. So it's a very good radiolaric mobilization. But very often we just surround a piece which contains these mobile radionuclides, so it's physically just surrounded with a good quality barrier that keeps everything inside. So I admit that you saw this, when we select a waste form, then we are looking to some criteria, how to select a good waste form. And there are here 7 important factors that are everywhere considered when selecting the waste form. So the experts are looking first to the waste loading. We want to put as much as possible waste in a smaller volume. So waste loading is very important. But then we are looking how easy it is to produce the waste form. So it's a parameter. Then we are looking to the durability of waste form. We need very durable materials to ensure that for a long time, everything is kept in place and the release is minimized, so it's reduced to 0, let's say, almost. But when we speak about millennia, then 0 is unachievable. Then our materials are radioactive. They are slowly decaying. During the decay, they continuously irradiate everything around, and first of all, the material, the matrix that keeps the material there. So radiation stability can become very important. I have many, I say anecdotic, but history from the practice it's just to explain to you that, let's say, some of the materials initially when you manufacture in a laboratory or even a factory, they are extremely durable, very good. But with time, due to irradiation, due to these slowly occurring effects, after several decades, they are almost good for nothing. They start to transform in powders and decay and decompose and so on. So that's important for us. It's something specific only for nuclear. Chemical flexibility says that our material should be able to accommodate a mixture of radioactive and chemical constituents, which are also present in the waste. Then number 6, this is particularly important for long-lived. So availability of natural analogs. We should judge about thousands and thousands of years ahead. And if you have in nature some of the materials that still are here survive, most important that they already contain, let's say, some natural uranium, thorium, something which is still there, they can serve to us as a kind of indication that our materials, being analogous to them, also will be able to stay for the future. And the last is compatibility with the disposal environment. So our materials, let's say cement. If you are dealing with the cement, materials made out of cement, perhaps you know that the pore water, the water which is in contact with cement, it becomes a little basic. The pH of this water goes to the basic regime, so it's in a fresh cement, it's maybe even 14, then about 12, etc. But it's such. And then, if your disposal environment doesn't like high pH environment, that means that the water in contact with cement starts, to eat, in simple words, but to interact with the environment and like poison. So it will not be anymore a barrier. So that one is also very important. So these main 7 parameters are accounted. So I already demonstrated to you this picture about the waste forms. So depending on the classification, my first lecture to you, of radioactive waste, nowadays we already know the range of materials which are used already and recommended to be used. So to the vertical direction, the activity of material increases. So if you look to the upper part, then really very durable materials are used. So glasses, ceramics, metal containers, these are very durable materials. If the activity is a little bit lower, then you see that glasses, of course, but then you get bitumen, cements, geopolymers, some high integrity containers that can be made out of high density polyethylene. So other range of materials are also used. And then we get to low level waste. Here, the main material is cement, cementitious materials, and it's mainly the topic of this lecture. And then very low level waste typically doesn't need any special immobilization because the activity there is very, it's a little bit higher than exantrum, so it's not much dangerous. And now this table, I saw in these papers that are on the table, perhaps you already worked with that. So I guess that the table is known to you. So these are main materials. The table is taken from this publication, from this book. What is in line is the report prepared by the National Academy of Sciences of the United States, which can be found in the internet or download. It's a very good book. I was one of the reviewers of this book, so it's very familiar to me. And in line is the IAEA, a publication on policies and strategies where you get, some high-level recommendations, indications, rather than exact details like in these publications. So here it's about features, about limitations, and when you produce a waste form, often secondary waste is produced. Some waste which are produced during this manufacturing process. So this column they contain, and it's of course needed to read everything here. But I will not bother you very much with the text because you got it there, and you have the possibility to look to the text a little bit later. So glasses, ceramics, glass composite materials, which is a mixture of which is a mixture of vitreous materials with some embedded crystalline faces there. So that's called glass composite material. And by the way, in your kitchen, every one of you have these glass composite materials. You know, the upper pan of ovens in your flats is, I'm sorry, someone is trying here to call me. I cannot speak now. They are, because these glass composite materials, they combine better parameters, the best parameters of glasses together with the best parameters of crystalline faces, and as a result, you can spill some cold water on the top, and everything it is as is, and it's very durable. So cements, bitumen, and metal. So here are the parameters. So a very important parameter chapter in my lecture. Please pay attention to it with a couple of equations, which is very important for both regulatory and operational stuff and so on. So what is that about? About retention of radionuclides by the waste forms. So when we will put our canister into the repository, it will stay there for here 100, 1,000, 10,000 years. This time the canister, even made of stainless steel, will corrode, and then the water will be in contact with the waste form. So we need to look and to know how are radionuclides kept retained in the waste form. And the situation here is such. So in this picture, you got, let's say, a piece of the waste form. In the waste form, you get a concentration of radionuclides. So it's W with this index I, which is for radionuclides. So maybe it's the concentration of cesium, 137. Then this piece is in contact with the water. This time, we will start detecting in the water with the concentration Ci some radionuclides. We will measure and we'll know. The point here is as follows. If you will increase the concentration in the waste form an order of magnitude, we will get in the water more. And the problem that appeared at the beginning of investigations was as follows. In one laboratory, they took a very little amount of radionuclides, got a very little amount in the water, and said, I manufactured the best waste form in the world. There's practically no here contamination. In another laboratory, they took 1,000 more radionuclides. Naturally, in their water, they got more in the water. When they started to compare to each other, it was a controversy, because if to judge only on the contamination, then that the last one is good for nothing and the initial is very good, which is not the reality. So it was introduced the notion of normalized leaching rate, not real, normalized. There is a normalization. So the definition of this normalization rate, it is given here. Of course, that I tend, to explain everything in the equation and so on, to pay your attention to, maybe not to bother you too much. The most important is that it is everything in the normalized rate divided to a parameter which is termed Fi. The definition of Fi is the relative content of radionuclides. So you get this normalized rate as a real one divided to this parameter, which is a small one. Because look, you divide here the weight of radionuclides to the weight of the whole block. And the weight of radionuclides is a tiny, small figure. So this number is a very, very small one. Because of that, when you calculate this normalized rate, you divide a number to an extremely small number. And naturally, you get a big number, right? And because of that, please pay attention. When you read in the papers, leaching rates that are of the order of, let's say, 10 to minus 3 power, this is normalized. The real is not minus 3. The real can be minus 10 or even smaller. And I will show you some numbers. So, but here is to pay attention. If you feel that you want to know more, just ask me. So I will, explain more and more to pay attention to that. So now, there are a number of so-called test protocols. Test protocols. They are already internationally approved. All laboratories use these test protocols. The reason of that is to be able, to communicate to each other. I'm following this test protocol, you too. Then we can, change the data. Otherwise, everyone does what he likes. So they are here, the main. So you see the very first one below, it's ISO. It's even of international standard organizations. But the structure is the same as of ISTM, which is the American Society for Testing the Materials. And that's for cement. This one is for cement. And then there are other. Among them, there is so-called PCT, this one. So it's the performance quantity test, what is ASTM, this number, C1285. When the experts started to work with durable materials like glasses, ceramics, if you put these materials into the water, there is practically no contamination of the water. The material is so durable that the water cannot extract. You need years and years to wait until a little bit something will be extracted from that. And in order to accelerate extraction, in this test, the material is crushed into the powders. So fine powders, so you take the powders, a very large surface area, put water, then you are able to measure something into the water. This is the reason. Yes, please.
Excuse me, if we try to measure the surface of the water, we will put our solid materials, radioactive solid materials in the pool water. If we try to measure the surface of the water, what about the background of radiation in the surface of the water?
First, everything, it is described in the test protocol. They are exactly written, everything how you should do, absolutely everything. And if you use later, in Russian Federation, instead of this ASTM and so on, they are so-called state standard, cost state standard. When again it is written everything to the point that if you want to measure the concentration of cesium, you should use then the next test protocol, standard, GOST, etc., etc. So your now concrete question, you asked if you want to measure the background radiation.
Yes,
I'm sorry, this is not done in such a way. So you exactly find the content of radionuclides in your waste form using specific test protocols, etc. Or maybe you initially prepared your metric in such a way that you took a certain amount of radioactivity, clean material, so it's because everything is here, it's not, evaporated, etc. So you know it. Then you take your water, you evaporate the water, you take the target, go to the laboratory, measure the amount of cesium there, and then recalculate the concentration of radionuclides in the water. So it's not that you take this water and measure and the background is interfering. No. So everything is done in a very exact, specific way as described by other test protocols. Okay, so here, these are the main, and there are different, the last one is even so-called VHT, so it's wait-for hydration test. When you take a very high temperature, again, in reality, that doesn't happen in a repository, but you do that in order to accelerate extraction of radionuclides from the material because it's very, very durable. So here it's again to pay your attention that was about normalized leaching rate. The real leaching rate, it is done using that one from literature from papers is NRI, and then is multiplied by the concentration of radionuclides, if you want to know it in becquerel per square centimeter per gram. So that's the equation to find the real leaching rate. So everywhere, in practically in all the papers, reports, etc., these are normalized leaching rate, not real. So these are again normalized. Just as a reminder, the real there, the equation. So on vertical is this normalized leaching rate, and here some specific pictures. These columns that show the waste for materials. So the first one is calcine. If you take from liquid radioactive waste the salt, remnant salt after evaporation of the water, calcine them, that means heat treatment until decomposition of the salt. So instead of nitrates, you get just oxide. And then oxides in the water, you see the leaching rate is very high. If you put them into a cement, depending on quality of cements, composition of cements, etc., you can obtain a range. The bitumens are much better. Phosphate glasses can be extremely good, but it's a range. These are the main materials of nuclear industry, high-level waste, borosilicate glasses. You see, it's again a range. And ceramics. So you have many times that the synrock, let's say, so synrock is here, but the ceramics can contain different phases, and some of them almost immediately dissolve into the water. So it depends on composition. When you manufacture a ceramic, if you a little bit miss stoichiometry, you get the main material with some secondary phases, and they can keep the radionuclides and then easily dissolve into the water. So you will get there on the top. So that's the idea to explain to you. So I finished with this introductory part, and now cements. So only about cements. So in the cements, we are dealing with the hydraulic cements. So hydraulic cements, hydro means water. So these are the materials, inorganic materials, and they have the ability to react with the water. Typically, not typically, but for cements, at ambient temperature conditions, no increase of the temperature, no additives, and they form hardened and water-resistant product, which is termed differently. So in States can be siltstone, pest is another, cement stone. So this is the terminology used for already hydrated cement when you got this solid material, the walls of the buildings, etc. So the cement itself, it's a binder. So it sets, hardens, and also adheres to other material to bind them together. And here, just to know the terminology that cement without or with fine aggregates, then you get mortar. If you add the sand and gravel, then you get concrete. So there are here 7 advantages of using cements in nuclear waste immobilization. They are all important because it's simple. It's low cost. Number 2, it's suitable for sludge, liquors, even organic liquids. If these organics, you emulsify them, so you make small droplets, and the other part is water, then this emulsified organic liquid can be immobilized into the cement. Then good properties, stability. Number 4 is alkaline chemistry. In reality, alkaline chemistry is very good chemistry because typically the radionuclides in an alkaline conditions, they tend to precipitate. You remember my lecture on auto treatment processes. And do not dissolve into the water. It means that it's good for immobilization. Then it's not burning, non-flammable number 5, good, relatively good self-shielding, compressive strength, so it's easy to handle. And this is a fragment of the table that you already saw. It is only about the cement. So there are the features like advantages you see here, high flexibility, low cost, etc. Limitations, because typically the waste loading is not very high, typically. Some of the radionuclides, they are retained not very well in the cements. So because of that, low level waste is basically cemented. And compatibility with organic materials is also not good. High salt content is not liked by the cements. Just a couple of slides without many comments from me about many cements themselves. So they are manufactured using high temperature processes, and there is an overall now trend to try to find substituting materials instead of the cements to not emit so much CO2 gases, etc. So let's leave that a little bit out of here. If you look to the cement powder, which is not yet interacting with water, then the typical Portland cement is composed of these oxides. So 60–65%, this is oxide of calcium. Then you get 20–24 silicon dioxide, then alumina, ferric oxide, and some impurities that can be even up to 4%. So they are given here. But basically, the composition of cements, of many other materials from this family, are given in terms of these triangular diagrams, where on the basis of these three oxides, it is shown the areas. So TC is the area of the Portland cement. BFS, fly ash, blast furnace slag, it is shown because these are important additives to the cement, and not only nuclear. But the table is more exact. So you see here, typical composition of Portland cement on oxide basis. You see the range of oxides, and then you see minimum, average, and maximum. So for the cements, it's not something, very strict. It's range. It's a range on oxide basis. In the cement industry, in the area where the researchers, so science as well, is working with the cements, because of so many oxides and long equations, the experts use abbreviations. So you see here the abbreviations used in cement. So instead of writing calcium oxide, the people write C, and this is not carbon. This is oxide of calcium. Then you see, instead of writing dioxide of silicon, they write S, and this is not sulfur. This is, and so on, you see. So these are notations, so and so on. So then some of the written equations look, for the people who don't know these notations, look very strange. But colleagues, in reality, the cement powder does not consist of oxides. I will finish the sentence and then you go with the question. It consists of minerals. So the minerals can be written, represented as a mixture of oxides, but these are minerals. So in reality, the minerals that constitute the cement are allied. You see here, this is tricalcium silicate. I believe you can see it's not so small on the screen. And then another mineral, it is called belite, which is dicalcium silicate. Then you get tricalcium aluminate, or is just aluminate turned tricalcium aluminate. And then there is a ferrite, which is tetracalcium aluminoferrite. And the notations, pay attention, in the bracket, these are the notations. So you see, it's different from that chemists use in there. and so on. So let me move to here and before. So it was a question in the room. Or it's finished.
Sir, in slide 26, slide number 26. So I don't have chemistry background, so honestly I confess that's why maybe it's a stupid question. There are many components which are all oxides are made of minerals like essentially aluminum, neon, carbon, potassium, and sodium, magnesium. But what's about hydrogen? These are the gases, carbon. The gases, how they use that?
It's not noted because it's here. H is used for water because in the cement there is no gas. It doesn't consist of gas. In the cements you cannot find free carbon. So there is no. So perhaps in situations, controversial situations, when in a research project or something.
In this case, carbon oxide is not as a gas, it's in a solid form, I think.
Yeah, but you see, calcium oxide is noted like carbon. Yeah, and there are situations, let's say, when carbon-containing materials are immobilized. So that is for irradiated graphite. And there can be a situation that is necessary to write everything in such a form that the people will understand you. So if it is a controversy, then in the brackets the scientists write, and explain to you that in this case C is carbon. So no one will be confused. But otherwise, if you work in the cements, instead of writing calcium oxide, they will write C. And then it's not really calcium oxide in the cement. It's the mineral, or can be CSH phase, so-called, that I will show a little bit later, which is a kind of torbermorite mineral, which is even such an equation, much longer. That's easily resolved. So to not confuse the people. So in situations when there is a controversy with the real chemical notations, the scientists write in the brackets what they mean, to not confuse the people. But that's used everywhere. So believe me, you'll take a report from any states, from Russia, and then you will see all these notations there.
That's why I asked about carbon dioxide in this case in its solid form in the cement composition. Carbon dioxide is not as a gas. It's like solid material in this case.
But which evaporates at room temperature, so will not be long time there. So
What does that mean?
yeah. But again, if something in a research project which doesn't deal with nuclear, but can be, again, if there is such a controversy, you just write in bracket what you meant, and that's it. So it's really avoidable. Or you write, instead of this notation, the real chemical equation. So that's not a problem. So okay, so you see here now for the mineral phases that I just demonstrated to you, that they are characterized by different properties. So if you take the phase which is allied, it has rapid hydration. It means very quickly interacts with water. So, but as a result, you obtain high initial and final strength. So very durable mechanical material. The belite mineral hydrates slowly, so not quickly, slowly interacts with water, but has a good final strength and has a low heat of hydration. Then aluminate also here, it interacts quickly with the water, releases a lot of heat, and ferrite slow and moderate hydration and moderate heat of hydration. And I will give you the exact number. So these are, but before doing that, colleagues, there are state standards in the industry, because cement is a material of the industry, and it is used on a scale such large that application for the nuclear, it's a very, very small percentage, even including the construction of nuclear power plants, because the cities are made of cement, let's say concrete, and so on. So everywhere standards are in place for the cement, and the industry is making available on the market the cements which are characterized by the name from the standard. So I put here, so I'm from UK, let's say, the British standard. And before this I consider stupid, but before this Brexit, that occurred, unfortunately, the British standard was the same as the European Union standard. So the cover, here is British standard, here it's written European standard. Maybe this time the British will transform this European standard into a national one, which again, there is no any need to do so, but who knows? So in the British standard, there are cement classes you see here from 1 to 5. And their names, but in reality, not to bother you, but if you open the standard and start to look there, you will see a lot of specifications. So from the British standard, you can find many cements which are specified. So in cement 1, you see here the column number 3, cement 1, and then other explanations on what is there added. So the limitations of content of one or another component, and so on. So that's the specification. The specification from United States is out of American Society for Testing and Materials. So they define 5 types of cements. And these types of cements are specified in terms of mineral composition. So you see here, tricalcium silicate. So that is not carbon 3 times sulfur, it's tricalcium silicate. Then decalcium silicate, tricalcium aluminate, tetracalcium aluminum ferrite, and other. And depending on the content of these minerals, you got cement 1, cement 2, cement 3, 4, and 5. And here it's a very generic specification of the cements, of their properties. So the first one is generic purpose, no any specific. But let's say number 5, it is when high sulfate resistance is required. So the cement number 5, it is used, let's say, in the case when you have some pillars, some posts in the seawater, where there is a lot of sulfur. And number 1 will be decomposed in a couple of years. That one will be there for hundreds, like in Viris, you know, for hundreds and hundreds of years without any decomposition and so on. So depending, so we say one word cement, but there are many different cements, very many. So here is the explanation what is meant under the type 1. So this is so-called ordinary Portland cement, type 2. So it's modified. Type 3 and type 4 and type 5 I just explained to you. It's, let's say, for seawater, let's say. So here it said monolith exposed to severe sulfate action. It has a slower rate of strength gain, so it's slowly getting the strength than normal Portland cement, but then it's very durable material. Let me see here. Let's say number 3. It's written high early strength cement. So this is a cement when you need you do some reparation works and you want very quickly to get a very strong mechanically strong material. Then you use cement 3. It interacts very quickly with water, by the way, underwater as well, and you get a solid material there very quickly. So that helps to select the proper cement. Okay, so for our purpose of immobilization of radioactive waste, very typically cements 1, 2, and 3 are used, very typically. But depends on what kind of the waste we are dealing with. Because in the case when we have some acidic waste, and that's operational waste, but can be your waste from decommissioning projects, because typically acids are used in decontamination. And then you get secondary waste liquid which contain acids. Then you will use the cement which is able to harden these acidic waters. So that shows just that everything, all kinds of waste, the first step is to characterize. Otherwise, you can get in trouble. So you know cementation is working, and you try to cement, doesn't work. Okay. So here in radioactive waste immobilization, modified cements are used, and here you see here the types of cements that are used by the nuclear industry now, what kind of additives are used. So this masonry cement, this additive in form of the lime, it is used when you get boric acid in the liquid radioactive waste, and the aim is to adjust the pH, so to increase it because it's too acidic, and the cements like basic solutions. Otherwise, it will stay liquid, no hardening. Yeah, and so on here. And by the way, just the last one is important because it's written Portland BFS cement. So Portland cement together with blast furnace slag. So in United Kingdom, this cement can be 10% is OPC, ordinary Portland cement, and 90% is blast furnace slag. And this is still cement powder, which will harden and produce a very durable cement stock. Okay, so now it's a micro photograph of this blast furnace slag cement from United Kingdom. You see there in this photograph pieces of blast furnace slag, like crystals inside of something, and something this is ordinary Portland cement which was hydrated with water. It's surrounding these pieces, and altogether this is a very durable material. So here again these three oxides, and where is the blast furnace slag there in terms of oxides, and where is the fly ash, and this is for OPC, ordinary Portland cement, the area where it's not a point because it's a range. I paid you attention in the table. And other here things are. Colleagues, in the generic industry, I noted to you that there is a trend to find substituting materials for the ordinary Portland cement. Yes?
So in general, whether the fuels are acidic or basic, nuclear fuels.
The nuclear fuels are solid. So
their byproducts are acidic or basic.
If you reprocess the nuclear fuel, then of course you use acids. So typically the liquids, high level radioactive waste, liquid radioactive waste, high level, these are very acidic.
So we need
but wait. But these high level radioactive waste are not cemented. They are everywhere immobilized using vitrification. So the water is evaporated, everything which is water, the salts are decomposed, and oxides there are fixed in a body of a glass. Because it's so high concentration of radionuclides that you need something more durable, more stable. So in this picture on classification, you remember on the upper part there were no cements there, only ceramics and glasses. In the very no.
SiO2 is in the top.
No, wait. Colleagues, about the materials, I will get quickly back, so don't worry. Here, you see here, depending on the class, high level waste, glasses, ceramic, metal containers, there are no cements there. If you decrease the content of radionuclides, then you can use cements. There, the durability of cements doesn't suffice. You need something more durable. So the people are using nowadays, and for about 50 years or something like that, vitrification, manufacture of glass with the radionuclides there. And even there are trends to use glass composite materials, with thin rock. You heard about thin rock? Perhaps you have some lectures here, but I'm not sure. So anyway, very durable material. So let's get back where we were.
But we took, yes, but we took pH value 8 to 12. That is a basic component. The pH value 8 to 12. In the slides, 2 slides, 3 slides before.
Yes.
So it means what is the main purpose? To neutralize the influence of acidity or somehow how it works basically.
I'll show you. That's the next chapter. So, but before going to the next chapter, just this table, it is giving you the impression, the information about so-called alternative cements. So even the industry is using calcium alumina sulfate cements and other cements. So maybe the last line, because in many research centers the people are working with geopolymers. So the geopolymers are also manufactured at a temperature which is a little bit exceeding the room temperature, so can be some 60, 80 degrees. And instead of the water, you need a very high basic solution. So with the water, you will not be able to produce the geopolymer. But otherwise, the geopolymers are very similar to cements. And there are in the literature, scientific literature, even speculations. The people from Egypt, there is a scientist in France, David Dovitz, he has books and he's spreading everywhere that he has some proofs which are not much believed by the scientists and so on, that the pyramids are made of geopolymers. So they were manufactured using powders, and then in place, using powder, you can build any height. Otherwise, how to explain this huge by mass blocks but who knows? It's something under discussion. So geopolymers are interesting materials investigated, but I'm not going into that material. I will. So you ask how it is done. Look how it is done. So let's say you get tricalcium silicate. It interacts with water. This is the chemical equation, and it's written stoichiometrically. So you see, you obtain something on the right hand, quite long, and then hydroxide of calcium, and then heat liberated, it is this minus because it's liberated. So 114 kilojoule per mole. So how interacts the calcium silicate? Then you get the equation of another mineral, the calcium silicate. You see much less heat liberated, only 43 compared with that. How quickly it interacts, I will also show in the next slides. So all these reactions are well investigated, well known how they do. And you see the next equation, how tricalcium aluminate interacts with water. It releases a lot of heat, 200 kilojoule per mole. If you take a cement based on tricalcium aluminate and make a drum which is about 100 or 200 liters, the heat liberated will be so much heat liberated that it will overheat, start to boil and so on. The heat of reaction is very high.
Exothermic?
Sorry?
It's exothermic or endothermic?
Very exothermic. They are all exothermic, releasing heat. Because of that, it's written minus. That means exothermic. And for that mineral case, the calcium aluminate, the release is the highest among other minerals. That's the main component. If you get much heat in your cement, be careful because you will not be able to manufacture big pieces, only small, otherwise they will overheat. Okay. Before going to how quickly they interact, so here it is shown the schematic of cement hydration. So if you look in terms of porosity, when it starts to interact with water, the porosity decreases. So initially the porosity is like, you get just powder, so porosity is almost 100%. And you finish with this fast stone where the porosity can be some maybe 20%, something very, very small because of hardening. And here, when you put powder with the water, not immediately you get the stone. There is a so-called dormant period, some minutes. And then there is a period of setting which is typically hours. So porosity is starting to decrease and some phases start to be formed. So you see that one, which is pure calcium hydroxide. This is a crystalline material which is called Portlandite. Portlandite, very important in the cement test because it gives to the pore water high pH, which is good for retention of radionuclide. And the most important for cement is this CSH phase, the most important one, which is amorphous, like glass, is not crystalline. Okay, that was in terms of plots. Physically, that happens such a way. You got water, you got these cement powders that they are not mineral, they are mixture of minerals. They start to interact with water, forming these components that were shown to you in previous slides, these chemical equations. And that grows in size. Because of that, the porosity decreases. And in such a way, the cement stone is formed physically. Oops, yeah. So here is the kinetic. So if you look to the degree of hydration for all these phases, you see that there are phases like decalcium silicate that indeed slowly interacts with water. Tricalcium silicate much quicker. Tricalcium aluminate very quick. It is the mineral which gives a lot of heat, so that heat helps to accelerate the reaction, so that they interact with water very quickly. Again, physically, how that happens. So that's from scientific papers and so on. So it's shown here that when the grain of the cement interacts with water, the CSH phase, which is amorphous, is formed, but also some crystals are formed. Because of that, they are shown here schematically as some needles. So this is Portlandite, but there is another mineral which is called ettringite. So they look in form of crystals, not amorphous material which has no shape, let's say. And here is the overall table that for these basic compounds of the cement, you see reaction rate, amount of heat, strength of phase that you produce, and degree of heat liberation. After the hydration occurred, you get the cement stone. And it is made out of other phases. What are these other phases? It's a crystalline phase, ettringite. And you see, the notation is just AFT. Nobody says that and use this equation, chemical. Otherwise, it's too long to write. So they say of AFT phase, the amount of heat is that and that and that and that, and so on. Then there is AFM phase for monosulfate, for hydrogarnet, for Portlandite. It is just CH. That's Portlandite. And then the most important for the cement stone, not for geopolymers, only for cement stone. It is the CSH phase. CSH phase, which if you take a XRD, so X-ray machine, and look to it's amorphous. There are no crystalline phases there, but the hump, where is the amorphous phase? It is where the tobermorite mineral is. Because of that, it is called also tobermorite gel, because it's not crystalline phase. Here again, mineralogy of hydrated Portland cement for your information. So you can get the reference here. Okay. So colleagues, I noted to you that for nuclear industry, particularly in the United Kingdom, but not only, the composite cement, which is made out of blast furnace slag, can be up to 90%, but typically is about 70%. And then the rest, so 10% is ordinary Portland cement. And if you compare, then you'll find, for example, that the pore solutions in OPC, you see, freshly prepared cement, 13.5. In composite cement is lower, it's only 11. When you immobilize a material, let's say some aluminum waste, which doesn't like high pH. So in the ordinary Portland cement, you can get big troubles, because immediately will start to interact and form products of hydration, of interaction. So blast furnace slag, it's better. It's a little bit lower by pH. It means that all these reactions will be with much lower rates. So it's also a feature of this blast furnace slag cement. Apart from that, it is better by all parameters. This table is also useful for utilization in research projects and in industry as well. Typically, to analyze what you have in your material. The thermal events are used. So you put in a furnace a piece of the material, and you are looking to the release or the consumption on the heat. And when some reaction occurs, you see on thermal cover some change. So here it is shown when the calcium silicate hydrate CSH gel starts to decompose from 110 to 120 degrees. When the ettringite and other phases, they start to release the water or to decompose. And based on differential thermal analysis, you can judge about the content of these mineral phases in your cement. So that's useful. That's maybe even taken from a scientific paper. It's something useful for practice. Colleagues, I noted to you these kinetic curves of hydration. So it is typically the standards require 28 days, and only after 28 days you can say that the hydration it's finished. I can investigate this material. But in reality, the hydration doesn't stop anywhere. It will go forever, but the rate of hydration will be slower and slower and slower. So, for example, in United Kingdom, in China, they have an older. In United Kingdom, we got a wall, which was built 2,000 years ago by the Romans. And it was made using Roman cement. We can take a piece of cement from there and find unhydrated phases of cement and know for sure the composition of that cement from that time. Because a part of the cement is still unhydrated. So it is believed that after 1 year, 12 months, about 95–98% is hydrated, but the remnant will hydrate with a slower and slower and slower rate. So it says also here that after 1 year, we get this cement stone, this pore water, which is contained in small pores. And if you will extract this water, we'll be able to measure the composition of this water, the pH of it, and so on. So this is a heterogeneous material. And once again, for cements, the most important is the tobermorite gel or CSH phase, which is like a kind of glue. So it's like, it's not exactly, but it's like a glue which keeps together all kind of these particles there inside. So that's for the composite cement BFS, these pieces of BFS surrounded by gray areas. And the amorpho phase, it's very difficult to investigate it because it doesn't show anything in XRD machines, and there is no diffraction. It's amorphous. So it's difficult to analyze it. Okay. So some 10 minutes, I think we still get. So technology now. In using cementation technology, it is one thing when we are cementing solid radioactive waste. But very often and very typically, we use cementation for liquid radioactive waste. And most often this is water which is contaminated. So we are interested to bind this water. And we are interested to bind as much as possible water. So the intent is to use a lot of water and as little as possible cement and to make a cement stone. But if you increase and increase the content of water and decrease the content of cement, we can get to the situation that no more able to manufacture anything decent. So colleagues, see here, it is shown the conductivity of a cement paste, which is formed as a function of water to cement ratio. So if you move into this direction, we get more water and less cement. So we want to put more water. But you see the conductivity increases drastically. So we should stop somewhere. And here it's to explain the definition of what is conductivity of the cement. So if you get an engineering, so perhaps you heard about this Darcy law. It is when you have a bed with the thickness H capital, and you put on top of it H small water, this water passes through the bed. And Darcy laws show how much water passes through your bed. So the bed is made of cement. And this coefficient, if it is a small one, means very little water is able to pass through. So we are interested to have a small conductivity in our case of immobilization. Otherwise, the water will leach out everything from there. So you see here, depending on the age, so the first line is age in days. The second line is conductivity. So initially, it's very high, but the porosity decreases this time. Hydration involves more and more material, porosity decreases, some of the pores start to close. So ultimately, it's a very slow conductivity. Then useful information here about the impact of hydration reactions. So anionic and cationic in red. It's cesium, for example, it is present here. So cesium, which is present here, you see it is here. So it's easier to bind cesium into the cement than sodium, and so on. So if you use as a simulant sodium, and you get a normalized rate which is good, then for cesium we can expect even better. So because of that, these lines are useful for knowledge, for simulating experiments, and so on. Because many of these studies are done using simulants, not for many reasons. Okay, so here it is shown about the reactions which occur between the cement and waste components. So typical waste components, so borates can be, and so on, different here. So let's say the line which is about flocks. These are the flocks that I explained to you in the method of water purification, precipitation. So these flocks that are sliced from water treatment process, and then on certain action, they can retard hydration. So you can get in trouble when you immobilize this material. So it's to give you advice what to do. And then the next table shows to you what to do if you get in trouble. So modifiers are used. So typically high molecular weight organics, they are termed super plasticizers, are used also in industry, not only in nuclear. The aim is to reduce the viscosity of the grout. So let's say if you immobilize the solid radioactive waste, there are some gaps in between the solid, and you want to put cement in between them. Then you add a little super plasticizer. The grout is very mobile, viscosity is very small, so it enters everywhere and quickly before the hydration reactions solidify everything, and you avoid big empty spaces inside, which is not good for the future. Because in the future, water will be there, and the water will start destroying everything there. So that's about what to do, what kind of modifier to use, and with which purpose. So the last line, let's say it's written here: ash, fly ash, natural pozzolana slag, which is blast furnace slag, to reduce heat evolution. So in United Kingdom, on the Greek side, we are using very, very big containers. They are several cubic meters, so large masses of cement. And we are interested to have a slow rate of hydration. Otherwise, it will overheat quickly. Then blast furnace slag cement is the best because hydration occurs slowly, and heat is released gradually, and there is no any problem to manufacture 10 cubic meters in one take. Okay, so schemes of cementation. So the first one, it is when cementation it is done in a drum, and we use this method in UK, let's say, for Magnox waste. So we put solid waste into the drum, the first scheme, and here pour the cement, mix cement and water, pour everything, and not only in many places, but it can be that everything is prepared before pouring into a container. So that was already explained. That is to show you the scheme from United Kingdom. the photograph is not from United Kingdom, is from Czech Research. Is anybody from Turkey? Yeah. You are from Turkey. This is photograph from your Czech Research Center, where you get a nuclear research reactor. And in your radioactive waste management department, there is such a unit there. So during one IE training course, we took this photograph there. So it is shown the mixer there, which is mixing everything inside of the drum during the cementation. Okay, so, oops, sorry. So that's to show you example. So this is a system used. That one is continuous cementation. So the grout is prepared outside of the drum and is only then poured into the drums. That one, this facility, it is used, the schematic of this facility. I should have also photographs, but here the scheme. It is used by Rosatom, here not far from Moscow, in the institute which is called Radon, and they cement to get a solid with liquid radioactive waste. So they put into the drum solid radioactive waste, and then they prepare the grout using liquid radioactive waste. And then the grout is put here. This is vibrating everything to fill all the gaps. So that works in such a way, and the photograph of the facility is shown on the left. So it's from a book, but that's available physically in Radon, not far from Moscow, through Rosatom. That's from United Kingdom. I noted to you the large containers, large masses. It was important to have slowly hydrating cement. That's in UK again for Magnox waste. We use 500-liter drums, so half of cubic meter. This is also quite big in volume. So again, these composite cements are better than just ordinary Portland cement. If you compare by everything, including rate of hydration. So these are photographs taken in UK, where simulants, of course, are used to demonstrate during the visits how they look like, how they are prepared, and to explain the importance of barriers, etc. Maybe just to pay attention that here it's a lot of material, including aluminium, into the body of the cement. So it's important to avoid a quick interaction of the water, which is high pH water, with these metals. Dear colleagues, this picture I showed to you in my lecture on water treatment. And I noted to you that we use cementation in order to cement everything in Georgia, in Caucasus region, not far from Tbilisi, city of Tbilisi. And the link, it is operational and is open access. It means that you will get access to it. Okay, so I'm closer to the end. I personally work a lot with the cements, mainly from the point of view of long-term durability. And that was a repository which was an experimental one in Radon institution, not far from Moscow, where operational radioactive waste from nuclear power plant were immobilized in these blocks. They are small in size, so the question is about some 30, 40 centimeters, half a meter, let's say, cubes. And they are manufactured in such a way with the purpose of investigation. And after 40 years, we opened the repository, took all the samples out of there, took samples from the outer parts, from inside and so on, just in order to investigate and to be able to judge about the rate of aging of these materials. This is the table taken from the state standard in Russian Federation on cementitious waste forms. And you see here, in Russia, the aging rate should be not higher, means less than 10 to minus 3 power gram per square centimeter per day. This is normalized rate, not the real one. If you calculate the real one, you should add there minus 3 and maybe minus 10 will be minus 12 and so on, because it's normalized. The real content of cesium in the cementitious waste form is extremely small. And we normalize this rate, dividing to the relative content. Pay attention, this is not a real one. You see here the requirement for mechanical durability. So in Russia is 4.9, about 5 megapascal. In construction, the requirement to compressive strengths are much higher because some of the buildings are very tall. The Ostankino, this tower is half of kilometer. So there, the cement is much more durable, of course. In France, let's say, instead of 4.9, it's just 0.3. Because what is the reason to have a high durability? The waste form is inside of the container. In the UK, is about 10. So it's not the same everywhere. But there are requirements to the waste form. And you see here also radiation durability, freeze-thaw cycles, and durability to long-term immersion into the water. And just again, you see here that relates to your question. Here the test protocols, testing method, in order to identify. But recently we had a meeting in IAEA, and that's table from Italy. And you see here it's much more populated compared with my table. And here it's compression strength curve line, and then thermal cycling, radiation resistance, and so on. So in the last column you can see. So in Italy, let's say it's also something like 10 megapascal. So it's requirements for sorry, it's 5. It's like in Russia. I should look to the big one. But in UK it's 10. So here the test protocols that are used by the nuclear industry in cementing real radioactive waste. Here about the aging processes that are investigated, what's happening with the cement when it interacts with the environment, specific action to the cement table. That table shows how behaves the cement in different soils. Because the water and soil depend on composition of the soil. Some soils contain sulfate, let's say. Then you should use the cement, which is durable, in water with sulfates, and so on. So going to the very end of the lecture, I found somewhere in the literature that a law in Roman Empire, long time ago, millennia ago, required not less than 200 years of ensured lifetime for aqueducts to transport the water. And we see through Europe that the remnants are still here after thousands of years. So if you follow the standards, then we are getting typically good results. So the conclusions that cementation is the main immobilization technology for low intermediate level waste. And cementitious waste forms are durable materials which provide a high degree of environmental safety for low intermediate level waste. And some useful references about cements. And here, colleagues, if again, the people from Egypt, this year we published together with Professor Abdel Rahman from Egypt. This is our second book for the cements, published by Elsevier, which has this long name title, and it's a collection of contributions from not just from me and Professor Abdel Rahman. Many researchers also submitted their chapters and are published in this book. So for the details, things are now available in publications. So with that, thank you very much. Yes,
Can I ask a small question? In one of your presentations, you mentioned that there's no second West if we use cementation for West immobilization. So what about all of these components that you show us that we use for cement immobilization? They are not also decontaminated?
In reality, it's written no secondary waste, and then in the bracket is written almost. in reality, in a real work, this cement as well, secondary waste is produced. But compared with other methods, then intentionally, not intentionally, but deliberately, let's say, we produce some liquids, some filters, and so on. In this case, some after decontamination, some remnant pieces, so some small amounts of secondary waste are inevitable. Because often, it's necessary to extract this mixer pedal and to clean it. And then what to do with this? It's secondary waste. So the volume is unpredictable, it's very small, but in reality, it's present as well as in other methods. So yeah, if you work.
So we can try to convert this radiation to energy, right?
Okay, so thank you.
Thank
you very much.
Oh, yes.
Sir, can we go to the slide?
Oh, of course. But yes,
So
they should distribute to the world. So we don't get
Sir, this
yes, we put it in the water. And if here it's a very small amount of radioactivity, then the water is also very small, right? You do that.
Да, потому что
in here, 1,000 times more radioactivity. Put into the water. And I see it in my water, What of radioactivity? Does that mean that your material is better than mine? No, because yes, in order to avoid this impossibility to compare, the people introduced normalization. So you take the relative content of radioactivity, calculate it, and calculate this normalized rate. I am taking, but my number will be 1,000 times
higher than mine.
Yeah. And then our numbers will be the same. And we are excluding the increase of that. It is like taken out. So this normalization is done in order to be able to compare.
Okay.
But in the future, when the people from your side will say, that's okay, but I need to know the real rate. Then you say, take this normalized, multiply by the real content, and you have it. You are restoring the reality.
Irrelevant to the concentration.
Yes, exactly. You restore. So, but the people use normalized.
So that we can have
in the test protocol is written.
So that we have a common platform to compare and contrast.
Only with this purpose. Because at the beginning it was discussion
like a mess.
It was a mess.
Because if you give me value with respect to your scenario, and I don't know what is the
that was 50 years ago, 40 years ago.
How I compare my status with respect to your numerical values.
Now there's a protocol of normalization.
So that this value is meaningful to compare with respect to any.
Thank you for your nice presentation, Professor. And this makes me so excited about to convert the radiation into energy. So all this energy underground, I believe, it will be very nice idea if we can to convert this gamma rays like neutrons, the concrete. What the kind of radiation becomes as a secondary radiation after simulation process, like gamma rays, beta.
They are shielded very well.
Yes, and neutrons, but it will be secondary radiation material. Yes.
Practically no.
No.
No, in cementation no. You get very little. Maybe your mixer is because dirty, let's say, it's contaminated.
And also in glass.
In the glass, we get liquids, filters, so it's a high temperature process. What you want? Much more. When you work with this material. What do you want to ask?
Do we have any material to monitor real temperature?
Nobody does. That question. Yes, there are such publications. I also published many papers. If you look to the references, you will find them there. Don't worry, you'll find them. For sure. So here, yes, exactly.
My friend, flash drive.
Thank you very much.
Okay.
سؤال عبد الله انا اسف معذره
Without any
Михаил Иванович, так, я вот эту всю штуку распечатал. Наши, да, нет, не ставок, нет наши. Это наши. Да, да. Тут сейчас я не помню какого цвета. А есть синий, вот то, что вот и
что не напечатано.
Здесь? И вот тут, и вот тут. Ага. Так, я сейчас на втором еще.
И где-то второй там, да?
Да, второй и третий, да. This? Вы сейчас сколько времени можете?
Да, я хотел бы.
Все, сейчас я
На минуту.
Сейчас я буду.
Насчет Словакии.
Да, Словакия вот и еще поддержки. Сейчас я... А вы как понимаете? Do you mind taking picture with you?
Of course. You can send it to me.
Коллеги, добрый день, меня слышно?
Да, слышно. Smile.
Так, мы вовремя начинаем, через 3 минуты? Или у нас сдвижка?
Да. Сейчас, я думаю, буквально пару минут.
Может, мы пока испытаем вывод на экран презентации?
Never mind.
Okay, good.
Thank you very much.
Of course, send it to me. Okay, you got my email.
I don't put you.
حسن ونجلاء حسن.
Okay, good. Thank you very much.
Where is my car?
Why did you invite Olga? They were making
After Abdullah send me, I will send you one.
So it's here. So send it to the private. That's better. That's better. To the private. Okay? To the private is better. No more.
Роман, да, можете спускать.
Put it on Facebook. Then everybody will see.
Find picture.
Yeah, that's the easiest way.
Your phone, сейчас. Окей, я запущу Романа. Я бы хотел денежку передать. И вот пойдем там. На группе.
You have
Там же надо координаты дали, чтобы...
Да, лучше есть сейчас.
А я волновался, как?
Роман?
Давал или нет?
Роман, как слышно меня?
Мне карточку.
Слышно хорошо.
Что, может быть, тогда презентацию запустим на экране?
Окей. Okay, done.
Thank you.
Как будете готовы, тогда скажите, я всех посажу.
Давайте мы сейчас попробуем зашарить экран.
Ага.
Получится, не получится. Что-то у меня тут миллион этих. Секунду. Так, сделаем. Видно ли?
Да, супер. Так, все, я тогда коллегам говорю, чтобы садились. Dear colleagues,
I prepared it for you. But if you know my email, then no problem. You know it.
Yes, I do.
Last day to do it. So good.
Yeah, please. Roman? Roman, are you hear me? Yeah. Perfect. So, dear colleagues, I want to introduce Roman Voronov. He is our master student from this year. So, Roman, please.
Yes, hello, dear colleagues, thank you for thanks to the organizers for invitation, for kind invitation to make such a presentation. I would like to make this overview of nuclear decommissioning in Lithuania based on my own experience participating in such projects, and making overview from available information for those projects where I did not participate. But first, let me introduce myself, as I did not do this during the first day. So that's my picture. I'm on the right, and my background was far from nuclear energy. I'm a Bachelor of Business Administration and Master of Applied Mathematics. But since 1997, immediately 1 year after graduation of the bachelor studies, I was working at Ignalina nuclear power plant, and my main area was probabilistic safety analysis, fire hazard analysis, and actually until now I work in this area as a researcher of Lithuanian Energy Institute. But after early shutdown of Ignalina nuclear power plant, I moved to decommission projects and started participated in many projects. We're working for a number of companies. So here you can see on the slide only several of them, and also participated in new build, this namely construction of solid waste management facilities at Ignalina nuclear power plant in Lithuania. So it's actually a project which is how to say, it's in between the decommissioning and the new build. So, and usually these projects are very closely related. And now I'm working as a private consultant. I'm a founder and director of a small enterprise, Radio Delta, which is at the moment it's a one-man business, but hopefully it will grow. My hobbies are kayaking, sailing, most of them, so related with water, with nature, and so on. So that's enough about myself, and the contents of today's presentation will be introduction about Ignalina nuclear power plant, then a decommissioning strategy chosen for this waste management and infrastructure for the decommissioning projects, current progress of the dismantling, new projects which are in front of Ignalina and PP, and summary and some observations which could be useful, I believe. And as I said before, because I am not official employee of Ignalina nuclear power plant, so my this lecture, this presentation, it is built on open available materials and my own experience. So let's start with the only nuclear object in Lithuania. It's Ignalina nuclear power plant. And first question, where is it? Where is it located? Where Lithuania as a country is located? Because it is a small country, and it's usually first question when they say that I'm from Lithuania. Where is it? So it is on a Baltic coast of the Baltic Sea. You can see, so this is close to, it's bordering with Poland and Belarus and Latvia and Russian Kaliningrad area. So, and you can see, by the way, do you see the mouse pointer?
Yes, yes.
Okay. And actually on southeast part of Lithuania, on the very border, you can see on this on a top picture. So this is the biggest lake in Lithuania, and actually Belarusian border is going on the lake. So it's the intention was to locate it as close as possible to Latvia and to Belarus. So it was built in Soviet time, and for energy supply to this western region of the Soviet Union. So Ignalina nuclear power plant contained two RBMK 1,500 reactors. So RBMK reactors became sadly known after Chernobyl accident, but actually that model was RBMK 1000, and there are I did not put this figure here, but there are about 11 RBMK reactors in 11 or 14 in actually former Soviet Union, including Ignalina NPP, Chernobyl in Ukraine, and Kursk, Leningrad, and Smolensk nuclear power plants in Russia. So yes, you can see the main figures. That's the nominal thermal power was 4,800 megawatts thermal, but after Chernobyl, it was a regulatory decision to decrease it, and the actual thermal capacity was 4,200, and the electrical capacity was about 1,200 megawatts. It's a boiling, so it's graphite, moderated, water-cooled reactor. It belongs to boiling water reactors. So that means that the steam after steam-water mixture, to be more precise, more exact, leaving the reactor is going to drum separators, and where water is and steam are separated, steam goes to the turbine, and then goes after condensation going by main is supplied to the aerators, and by main feed water pumps is brought back to the drum separators, and water from drum separators is circulating via the main circulation circuit. And as it is boiling type, it means that steam going to the turbine is contaminated with radionuclides, and the turbine equipment and turbine hall equipment is contaminated as well. Level of contamination depends on the equipment, type of equipment, but most of the compartments of the turbine hall was free access during operation, and only several compartments are either restricted or limited access during power operation. And you can see that actually Unit 1, the design lifetime was 30 years, of course, with possibility to prolong, but you can see that Unit 1 was shut down only after 21 years of operation, and Unit 2 approximately the same. Well, for us, I was working, as I said, I was working at NPP for 9 years, and for us, of course, it was big, very sad news, let's say. It was the decision taken by the government, but as I said, potentially the nuclear power plant could be in operation for long years. For example, Leningrad NPP, which was first of the RBMK type, its first unit was shut down only 2 years ago. Maybe I'm wrong, maybe 2 or 3 years, but only recently. So it's cannot be compared with such short operation time for Ignalina. So main parameters regarding the size of the reactor. And here you can see cross section of the reactor building. So yes, maybe okay. Very shortly. So this is the core of the reactor. It's channel type. It's 1,661 channels totally in the reactor core. The graphite is a moderator, as I said, and the flow is like this. So steam, I will start from the core. So steam goes up to the steam water lines. They're going to which then steam water mixture goes to drum separators, as I said before. So here you can see this primary main circulation circuit. These are main circulation pumps. Actually, there are two circuits for each 2 sides, let's say, of the reactor. And then it's returned to bottom water lines by the water. The water is returned back to the core. And this picture, we will see it in the end of presentation when I will see, not this, but similar when I will speak about the challenges and future projects. So, decommissioning strategy which was chosen. Immediate dismantling was chosen for. Yes, like this. And on the next slide, I will explain why. But okay, the main task was to use NPP operating personnel because we don't have a possibility to have separate specialists or separate companies for decommissioning, because as I said, it's the only nuclear object in Lithuania. And the dismantling of equipment and systems is implemented unit by unit, and I could even say that block by block. I will later explain the structure of the buildings and what's the difference. And as soon as nuclear fuel stays in the units, within the units, either in the reactor core or in fuel pools, spent fuel pools, the plant is considered to be in operation, and this means that it has operating license. And in order to perform any kind of decommissioning or dismantling works, a separate change of operating license is provided by the regulating authority, and for this a separate only after development of a separate decommissioning design and safety analysis, safety justification of such a dismantling, and only then corresponding license is provided, or let's say it's supplement to the operating license. And the decommissioning license will be issued and provided only after, should be provided, not will be, but should be, because again it's a question of safety justification. Should be provided after spent nuclear fuel is completely removed from the units. Current schedule is by the end of is to finish all the works until 2038. I didn't mention that actually a brownfield, it's a final state which is planned. So it was there were discussions either it should be a greenfield or brownfield, but so-called, and you already know what it means. So that means that buildings and some infrastructure will remain for the use, and the cost evaluated is almost 3 billion euros for the until the end of the project. And funding is provided mostly by the European Union, because it was also already described and explained by previous lecturers that usually a special decommissioning fund is introduced, and the cost part of the decommissioning cost included in the electricity price. But in Lithuania we didn't have such a fund. To be more specific, such fund was established, but it was too little time to have to collect or some significant amount of money. And as this early decommissioning or early shutdown was due to requirement by European Union, by international society, so European Union is therefore the main sponsor, the main donor of this decommissioning process. During development of decommissioning plan, there was a comparison of between immediate dismantling and deferred dismantling, and you can see the reasons why immediate dismantling was chosen. yes, I already said that using of personnel, INPP personnel, using of existing infrastructure for the waste management and decommissioning, lower total costs it was calculated, and no burden for future generations. But it's also related to question of personnel, because you understand that in order, if we choose this deferred dismantling, so we should keep competence of people, we should train new specialists, and it's not such a easy task. And arguments for the deferred dismantling was that lower cost is required the beginning of the process, and it was a possibility that some countries with RBMK reactors, I mean, of course, it is Russia mostly, develop some know-how, some technologies for treatment of irradiated graphite, treatment of the dismantling of the activated materials of the reactor core, and lower dose rates in the future due to decay of radioactive materials. So the general and very general decommissioning timeline, actually preparation for the decommissioning, let's say starting date for the decommissioning is to year 2000, when the decommissioning service was established at NPP, and the decision was taken for decommissioning. And as I said, of course, it was taken very negatively by the personnel, and in the end, maybe we can speak a bit about this psychological stress and this let's say tension of which people had due to this shutdown decision. And preparation for decommissioning have started, and you can see that many processes are overlapping, going in parallel, because you can see this dark blue arrow, the dark blue line, and as I said, that until complete defueling of reactors and complete defueling of units, this is operating license, and let's say post-closure activities started with post-closure, and more and more proportion or ratio of dismantling and decontamination activity, of course, was increasing. And also after removal, after the dismantling of equipment from certain buildings, demolition of such buildings also was started and is already going on. Not in a larger scale, but it's already, the process is already started. So waste management. In some on some of my slides, I just take copy pasting slides from Ignalina nuclear power plant's presentation, which are available publicly, so you can visit the NPP website and see the complete versions of these presentations. And such a picture, it's very good how to say, to understand the level, the amount of works of both units, and our I don't remember the author, but our communication people, communication service likes a presentation of quantity of metal to be dismantled in Eiffel Towers. There was also a figure about evaluation of amount of concrete in Egyptian pyramids, but I don't remember the figure, to be honest. I didn't find it, but there is such again such evaluation for understanding, for better understanding of the public. And yes, similar approach, but it's a layout, and you can see the structure of each unit. So reactor building, it's so-called block A. Block B is water treatment, and block V, so-called, it's a gas circuit. A gas circuit means that actually graphite stack of and the internal cavity of the Arbenki reactor is a gas is pumped, which is a mixture of helium and nitrogen. So it's not only a water circuit, but also a gas circuit. And the turbine hole is so-called block G. The letters here are from Russian alphabet, A, B, V, G, D. And between the reactor building and turbine holes, there is a control electric and deaerators block, blocks block D, D1 and D2 correspondingly for unit 1 and unit 2. And I mentioned before that block by block, unit by unit, and block by block approach. So actually, some these small tanks of emergency co-cooling system were dismantled first. It was, let's say, first approach, first experience of dismantling lightly contaminated equipment. And the second was dismantling of the turbine hole, which was also a challenge because of large amount of equipment, big amount of equipment, and the fact that the equipment was contaminated. And it includes turbine and condenser and condensate treatment system. Actually, most of it was contaminated lightly, but still contaminated. So it cannot be just free released, which is the case for pressurized water reactors usually, because as far as I know, dismantling of the turbine holes for example, for VVER reactors, it's usually very just conventional dismantling and demolition of buildings. So here is a picture presenting waste inventory evaluated. Maybe I will not go too much into details. You will have this presentation. You can check the figures later. Maybe I will try to update. Oops, sorry. This figure, which is actual amount of actual progress. And so there are operational waste stored. It's in the top. It's also known as historical waste, which was generated during power operation of the nuclear power plant. and then large amount of waste. This is decommissioning waste. So this is waste of generated from equipment to be dismantled from the reactor dismantling and from demolition of buildings. And treatment of such amount of waste required corresponding infrastructure, and the waste roads are shown here. So I mentioned operational wastes, and one part of this decommissioning process is retrieval of this historical waste. It's processing on a processing facility, or sending for low-level waste, intermediate level waste, and for very low-level waste, buffer storage. We just send to the buffer storage and to the landfill facility. And you can see red ones, red boxes are facilities which are under development and to be built, and the green boxes are those which are already in operation. Yes, storage. Yes, processing facility of low and intermediate level waste is the final destination point is either near surface repository or existing storage facility. And for the decommissioning waste, the waste route is a bit different. It is decontamination and size reduction of the waste of the equipment, which is now actually a waste, radioactive waste, is performed in the units. Now there is a decontamination and size reduction facilities installed in turbine hall, and being and on the site additional facilities. So this is this one, exceeding decontamination facility. And again, so waste, very low level waste goes to buffer storage, then to landfill. Free release waste goes to the free release measuring facility and outside to the free release. And low and intermediate level waste also goes to the same facilities, solid radioactive waste processing, and to storage or to near surface repository. And spent fuel goes to interim spent fuel storage. More details about these new facilities, about this infrastructure. So first of all, yes, interim spent fuel facility. It's actually, you can see how it looks from outside and from inside, and transportation is performed using the special railway platform from the unit, from block A, from the reactor hall to the facility. And actually it's a concrete compartment, storage compartment with corresponding biological protection, corresponding lifting equipment, and radiological measurement equipment. So the final stop for the nuclear fuel is a deep geological repository, which is now only at the research state. Sorry. And it is intended for spent nuclear fuel, but also to the activated metal structures of metal parts from the reactor, for the graphite from the reactor, used spent sources, and other radiative waste which belong to classes D and E. Waste classification was provided before. So this is actually a long-lived waste with so there's the same low intermediate level waste, but they're classified depending on short-lived nuclides and long-lived nuclides content. So again for spent fuel, graphite and long-lived waste. And main stage are provided here. So now only, as I said, we on a stage of investigate. I mean, Ignalina nuclear power plant. Lithuanian specialists and Lithuanian society on the stage of site selection, and it's important not only from technical, geological, but also from social point of view. So we need to speak with people, with population, and which could not be very happy to have such a repository on their backyards. Other facilities, we continue with overview of the waste treatment facility, and we start with waste retrieval. And waste retrieval facilities were provided for retrieval of the waste from old temporary storages. So work was performed remotely, and you can see this is how very low level waste is going to so it's the part is taken from this picture was taken from the cold trials of this retrieval facility. So these are not actual radioactive waste, but the imitators of the waste, but the process will be like this. So it will be a wall is cut, opening is cut, and using remote operating equipment, the waste is retrieved and further sorted and sent to either to buffer storage or for further processing. And yes, here is a picture of the facility, which is close to the existing temporary storages. So next, yes, and for very low level waste, final stop is actually intermediate stop is buffer storage characterization facility, so-called B19-1. It is in operation for 8 years already. It's located right at NPP site. It's indicated here on the diagram. And final stop will be landfill facility, which is not built yet. And on the photo there is how it's called. It's just a presentation of how it should look like. It's a model of such a facility, and you can see that it will be loaded with C containers, the ISO containers, so-called. Then it will be the containers will be covered with bales containing very low level waste, and then several layers of layers of isolation materials will be it will be covered by several layers, which is isolate the waste from outside impact of weather, climate, and so on. And of course, yes, it has a bottom support foundation which isolates isolate waste from the ground, from the groundwaters, and so on. Next facility is solid waste treatment and storage. It includes its complex facility. Unfortunately, I didn't find the better pictures. And the pictures which I have in my archive, I'm not sure that, so they are actually proprietary, so I'm not sure that I can use them. But it includes waste incineration, grouting, size reduction, sorting cells for low-level waste and for intermediate-level waste, so-called Group 2 and Group 3 waste, and to separate storage facilities. You can see them on a picture. So the storage facility for low-level waste in concrete containers, and for intermediate level waste, which are in steel containers, which are actually not have a function of biological protection, but only for the temporary storage. The biological protection is ensured by the walls of the storage facility themselves. So, and the final stop for such a low-level waste will be a near surface repository, which was designed, and the tender for construction is ongoing. So, too high competition. Everybody wants to have such a contract, and therefore this tendering process is going so long and very with a lot of claims and so on. And here I would like to highlight and to notice that actually the facilities which I have shown before, namely spent nuclear fuel facility, first of all, and secondly, it's a solid waste treatment facility, were actually bottlenecks for the whole decommissioning process. And this should be taken into account for the plants which are approaching the decommissioning, or even for new build plants. Because I know that now in the new build design, the new build design of new build plants, already includes decommissioning plan. Should already include decommissioning plan. And in our case, because we started this, it was not included in the design. We started to develop this design later, and the fact that we didn't have spent nuclear fuel interim storage facility. What does it mean? That means that we cannot remove and transport spent nuclear fuel from the units. It was taken from the reactors to the spent nuclear fuel pools, okay, for wet storage, but it's still on the unit. And as I said before, we could not obtain decommissioning license until fuel was on site. And it was really a big issue. So, and any delay of such infrastructural projects could delay the whole process and correspondingly increase the cost, duration, and so on, because you have to maintain to keep all safety systems in not all, of course, but those safety systems which are required, which are justified to be necessary while the fuel is on the site. You have to keep these safety systems. You have to keep the personnel, and you cannot involve this personnel, for example, to this decommissioning activities. So take this please into account when you are when you do such a project, when you plan this dismantling decommissioning strategy, decommissioning plans, and so on. The dismantling, decontamination, and dismantling, which we shortly abbreviation is D&D, what was performed. And again, this is a picture from INPP presentation. As I said before, decontamination, fragmentation, size reduction, and decontamination facilities were installed in the turbine hall. It was also a part of the project where I took part. And so actually these facilities were installed in the turbine hall after, let's say, some areas were cleaned from the equipment. These facilities were installed, and the equipment which was dismantled was going to the fragmentation, decontamination, and further to buffer storage. I mean, after not very low, but free release waste was going to a buffer storage. And here you can see so-called block D. No, it's not D0, sorry. Building 119, so-called. It was a heat plant, which was a boiler house, if you like, which was using the steam from the turbine for heating, for district heating. Actually, it was supplying hot water, of course, not the steam from the turbine directly. Of course, several intermediate circuits were used, but the hot water to heat the town, to provide hot water to the town, was generated using the heat from the turbine. This heat plant was used as a buffer again after dismantling of equipment, because the equipment was not contaminated. It was more easy, and it was used for, and it's used until now as a buffer storage for free release waste. So it's convenient to have such a buffer storage when you can make some preliminary measurements. You can sort, you can put them into the containers, and then just transport to the free release measurement facility for, let's say, final characterization and free release. And yes, after cleaning of the turbine hall number 1, the same, because turbine halls are located actually in the same, it's in the same building. So from unit 2, also turbine hall equipment was brought to these facilities for fragmentation and decontamination. But for the reactor dismantling of the reactors, which is not started yet, it's just planned. Maybe I should start with some other picture. So it's actual progress actual progress of the dismantling, and you can see that both turbine halls are already dismantling of equipment is already completed. These blocks D are also almost completed, so D2 is 98%. And but for the reactor buildings, it's in preparation or it's only in plans. And going back to the previous picture, yes, for dismantling of the reactor and primary circuit equipment, a separate facility was installed, and in the unit itself, and on the arranged on the site using the building of workshops, previous repair workshops. So again, okay, the progress is here, and how it's some pictures of how the works were performed. So you can see the equipment, cutting of the main large components. Here you can see the cylinders of the turbine. By the way, I forgot to say, if you have any questions, so please don't hesitate to ask them, either immediately if something is not clear, or if you want to clarify something. Or of course, we will have time for discussion, for questions and answers at the end. Is it okay? Can you hear me?
Yeah.
Okay. So yes, these facilities which I mentioned, located in the turbine hall. So yes, actually the area of main feed water pumps was used for size reduction facilities, and yes, and the area of okay, in the let's say western part of the turbine hall was used for decontamination and measurement. So actually, and these transportation roads were developed also during the project where I took part. So this is a progress of well, actually, you can see the picture of how the process of dismantling of turbine hall equipment was going on, and at the moment there are only clean surfaces, clean concrete floors, walls, and so on. Of course, some equipment remain. For example, service water, electrical power supply lines, which are passing through the turbine hall, of course, they remained as is. And it was also a task, and it's a tricky question, how to separate and how to protect the equipment which remain as is during this dismantling works, and cutting of equipment in situ and so on. And this also should be taken into account, and very detailed analysis of and the inventorization should be done. You should know what is located and where, because we usually had situations when we're going to sell, for example, a condensate purification system cell, and we start, okay, we understand which pipes are, what kind of pipe is there. Some kind of unknown pipe, and even operating personnel, they didn't know what kind of pipes there are. They know equipment which is there in their area of responsibility. And sometimes, yes, we were finding equipment which was not identified, that it was a task to identify. Could it be dismantled or not, or should we take some additional protection measures in order not to damage them? Yes, and the overall amount of waste is 18,000 and about 19,000 tons for each turbine hole for Unit 1 and Unit 2. And as I said, at the moment, it's completely dismantled. Very interesting engineering, let's say, decisions were taken, for example, for removing the rotors of the turbines. The rotor was removed in a whole piece using manipulating all turbine hole cranes. So some tasks were unique. So this is also pictures of works. Sorry. Pictures of works performed in this blocks D, which is controller electrical and deaerators blocks. And yes, it was the progress and new projects, new challenges, and new tasks which INPP is facing now. Yes. So with equipment of turbine hole, these deaerators, as well as gas circuit, ventilation, and so on, there were some tricky tasks, some challenges, but it cannot be compared to what will be cannot be compared to dismantling of the primary circuit and the reactor itself. So here you can see this 3D model. It's also extract from INPP presentation, where the primary circuit is shown. So it includes the primary circuit. You can see it in blue lines. So this gray, these are drum separators, these gray cylinders. These are main circulating pumps, and you can see these blue lines are steam water lines, water pipelines, and bottom water communications. And again, as I said, there are 1,661 channels, and for each channel has its own water supply and steam and water mixture pipeline. So you can imagine the amount of piping there. Here also we have so in red these are steam lines, and that part which is going from the drum separators, because steam lines in blocks D and G are already dismantled. And in green, as I understand, this is a emergency co-cooling system. Yes, these tanks accumulators were dismantled immediately. I mentioned this in the beginning. They are were located in small separate buildings, so they were dismantled in the very beginning. But that part of piping which remains on inside the block, inside the reactor building, it remains. And this white drum or white cylinder barrel, let's say, this is the reactor itself, and you can see that now in terminology which is used for this decommissioning purposes, it is divided to 3 parts. Let's say R1, these are steam upper communications, upper piping, let's say. Bottom piping is R3, and the reactor core, reactor shaft itself is so-called zone R3. So this is about the reactor. So this is 3D model how it is located. You can see drum separators here, the reactor shaft and the reactor cavity. And here's a historical picture of how this how it was assembled and delivered to the power plant during its construction and installation of equipment. Yes, also some pictures showing the overall layout, and at the moment there are tenders going on declared by announced, not declared, announced by NPP for engineering services related to dismantling of the reactor and corresponding structures, corresponding equipment. I think that in 2018 it was a big conference, and even series of conferences at NPP, where all interested organizations, all interested parties from all over the world were participating, providing their, let's say, providing their experience. So this is this tender has a very high interest in the world, in the decommissioning world. And another also related to the reactor dismantling is treatment of irradiated graphite. So the graphite which was used in the reactor cavity, due to content of 14th carbon, and due to, of course, it is radioactive, and the presence of 14th carbon, it's one of the concerns. So, and these projects, as I said, which are much more complicated and much more, and from the technical and from radiological, from safety points of view. So this is really a challenge for Ignalina nuclear power plant, for Lithuania, and for those companies who will participate as a supplier of such a design.
Excuse me, Professor. Excuse me. The previous slide.
Sorry.
Previous slide.
Yes.
Yes. So if the graphite has this kind of challenge, why not to use different kind of material like graphene oxide, or other kind of materials? Why not?
Oh, here I cannot answer you exactly, because as I know that different solutions were proposed but at the moment, no decision, no final decision is taken, and at the moment, the only option considered is temporary storage and then deep geological reposition.
Thank you.
Maybe during the project, some decisions will be proposed. Maybe some technologies will be developed, which could allow, because it's really significant, big amount of graphite.
Thank you very much.
Well, summary. Okay, we have, as I remember, about 15 minutes to the end. Yes.
Yes.
Okay, so summary and some observations. To summarize, yes, Ignalina nuclear power plant is the only nuclear object in Lithuania. So it makes not like in the countries which significant nuclear fleet as France, as Spain, as Russia, where this experience could be of course not easily, but could be transferred from one plant to another, where you can, where your local competence, you can have your own specialists and your own competence with strong scientific support. But in our case, we have this only object, and which after decommissioning, such experience could not be used in Lithuania, but maybe abroad for other countries, for other reactors. Yes, as I said, NPP decommissioning is funded in a major part by European Union, because it was their idea and their request to shut down the operating nice and newest RBMK type plant. So as I said, the radioactive waste management infrastructure could be a bottleneck, and it is it was developed, and it's still being developed in parallel with decommissioning, with dismantling and decontamination of equipment. And when we started design, and when we just started decommissioning activities, planning, choice of strategy, actual design, of course, we didn't have our own experience, and we used experience of Western consultants, from experience from Greifswald, which was mentioned last week, and from other countries, which already from United Kingdom as well. And I could say that NPP personnel have adopted such an experience and successfully continued to implement, to develop the design by their own. But now we are approaching, again, NPP is approaching a stage where our own experience is not sufficient, is not more working, and therefore external companies are invited for this dismantling of reactor. And yes, decommissioning is performed by NPP personnel, former operators, former repair personnel, and we use the experience and their knowledge, their qualification. And yes, as I said, that major challenges are dismantling of the reactor core and treatment of irradiated graphite. And some observations, which again, I just repeating what was already said. Infrastructure is critical, could be a bottleneck, therefore it should be planned and maybe started in advance, preparing to the decommissioning, and planned in advance, having in mind any possible delays, increase of scope, increase of price, and so on. Inventory data are very essential. I mean, inventory of both physical inventorization and radiological inventorization and characterization of equipment. So you should know every piece of equipment, where is it located, what are the properties, and so on. Again, experience of operation repair personnel is essential in again developing this turbine hall project. We used knowledge of people who was participating in installation of the turbines and turbine hall equipment, not only in operation or repair, but they remembered installation, and their experience was very valuable, because they said yes, how they did this and what you should do, just make this process in a different order, in reverse order. Transfer from operation, there is a very big difference between operation, usual day-to-day operation of the power plant, which is line work, and the decommissioning, which is usually performed in a project manner. And again, last week there was a very nice lecture on project management, on project approach to decommissioning. But these are completely different approaches, and the personnel should be trained and should be prepared for this, because it's also such transfer could be painful and could be and need also competence and knowledge and corresponding training and experience. And it's important to keep the personnel, because when personnel, and we also faced such a phenomenon that when personnel have all such a nice training in project management, in contract management, and they have experience in development of strategies, decommissioning strategies, decommissioning plans, and so on, they know some, let's say, some internal information. They became very valuable prize for headhunters. And yes, they could such valuable people, valuable specialists could have such a job offers from another companies. And it was already mentioned that the market of nuclear decommissioning is rising, is increasing, because more and more plants, nuclear power plants, approaching the decommission. So yes, such personnel will be very, very valuable resource. So thank you for your attention and patience, and questions, please. We have some about 5 or 6 minutes. If more questions, maybe our dear hosts will give us some more time. I'm sorry, I cannot hear. Maybe if you have a question, could you please come closer?
Thank you.
Okay, if there are no questions.
Okay, one of friends want to ask a question. Can you hear us?
But could you please come closer? Because it's difficult to hear.
Yeah, I'm asking these questions instead of Halit. He was a little bit shy. And he's asking that normally in the other reactors, like VVR, the turbine site is not radioactive. That's why it's not decontaminated or dismantling, because it can be used again and again. But for the reactor that you have, RBMK, is one loop reactor, right? That's why. Yes. That's why also turbine site is radioactive and contaminated. That's why. Therefore, you dismantling it. Just he wants to confirm it. It's correct, right?
Yes, yes, exactly. And as you said, for VVER and for other pressurized water reactors, yes, because they have this interim circuit. Yes, the turbine site is clear, and you can use. So this equipment could be reused. By the way, in our case, for example, we. Such equipment as generators, not the turbine, but the generators, it is clean. And after radiological checking of its radiological status, they were sold. They were sold to other plants, and so yes, it could be reused. But other equipment such as a turbine, and you could see these pictures of cutting the turbine cylinders.
Okay, thank you. And this is my question. That this is my real question. And you mentioned that the budget of this decommissioning is coming mostly from European Union.
Yes.
It was a topic actually that before we talk about that, the financial part of this decommissioning, and normally it should belong to operator company, right?
Yes.
So how you manage it that European Union provide this financial support?
As I said, actually, this requirement, actually, this closing shutdown of NPP was premature. It was earlier closing, and the decommissioning fund was established, but it was not sufficient time to collect significant and sufficient amount of money in that decommissioning fund. And as European Union was the initiator of this idea, and it was requested, it was not our idea to shut down earlier this nuclear power plant, as I said, which was the newest of our BMK series and the safest, and so on. And but it was requirement of European Union. Therefore, we said, okay, gentlemen, we could do, but who pays for that? And yes, they agreed to pay such significant price for this for the decommissioning project. And in such a case, organization and also you should take into account such a management of such a case, because you have they are donors. They providing you with money. They want to have detailed, complete reports about how the money are spent. You are always there is strict monitoring of spending money, of
I see.
the progress, and so on.
Okay, thank you.
You're welcome.
Roman, thank you very much for your presentation.
It's my pleasure.
Thank you. Bye-bye.
Thank you for inviting.
Dear colleagues, now we plan to have excursion in